Earth, our starting point, measures 12,742 kilometers in diameter at the equator. A sphere of rock, water, and atmosphere suspended 150 million kilometers from the Sun, the distance defining one astronomical unit. This distance represents the baseline for measuring the solar system and beyond. Light from the Sun takes 8 minutes and 20 seconds to reach Earth, traveling at 299,792 kilometers per second through the vacuum of space. Earth orbits the Sun at 29.8 kilometers per second, 67,000 miles per hour, completing one revolution every 365.25 days. The planet tilts 23.5 degrees relative to its orbital plane, creating seasons as different hemispheres receive varying solar illumination throughout the year. From Earth's surface, the solar system appears as points of light moving against the fixed stars, but the true scale extends far beyond visible planets. The solar system's extent reaches far beyond the orbit of Neptune, the outermost major planet, at 4.5 billion kilometers, or 30 astronomical units from the Sunday. Neptune takes 165 Earth years to complete one orbit, moving at 5.4 kilometers per second through its distant path. But planetary orbits represent only the inner solar system. The heliosphere, the bubble of solar wind and magnetic field surrounding the Sun, extends roughly 18 billion kilometers, or 120 astronomical units, before pressure from the interstellar medium compresses it into the heliopause. Boundary. Voyager 1, launched in 1977 and humanity's most distant spacecraft, crossed the heliopause in August 2012 at 121 astronomical units, entering interstellar space while still technically within the Sun's gravitational influence. As of 2025, Voyager 1 has travelled 24 billion kilometers, 161 astronomical units, sending back data about the interstellar environment beyond the solar wind's protective bubble. The Kuiper Belt, extending from 30 to 50 astronomical units, contains over 100,000 objects larger than 100 kilometers, including dwarf planets, Pluto, Eris, Makemake, and Haumea, discovered throughout the 1990s and 2000s. These icy bodies represent remnants from the solar system's formation 4.6 billion years ago, material that never coalesced into planets due to low densities and Neptune's gravitational influence preventing accumulation. Pluto, reclassified as a dwarf planet in 2006, orbits at 39.5 astronomical units with an eccentric 248-year period, its orbit tilted 17 degrees to the ecliptic plane. New Horizons spacecraft flew past Pluto in July 2015, revealing complex geology including nitrogen ice plains, water ice mountains, and active surface processes despite temperatures around 40 Kelvin. The Kuiper Belt transitions gradually into the scattered disk, a region of objects with highly eccentric orbits, scattered by Neptune's gravity, extending to 100 astronomical units and beyond. The Oort cloud, a theoretical spherical shell of icy bodies surrounding the solar system, extends from roughly 2,000 to 100,000 astronomical units, nearly halfway to the nearest star. This vast reservoir contains an estimated trillion comets, with total mass perhaps 5 Earth masses. Though observations remain limited to comets perturbed inward toward the Sun by passing stars or galactic tides. Long-period comets, those with orbital periods exceeding 200 years, originate from the Oort cloud, appearing as new comets making their first passage through the inner solar system. Comet Hale-Bopp, visible to naked eyes in 1997, came from the Oort cloud with a 2,000 533-year orbital period, and aphelion, near 370 astronomical units. The Oort cloud's outer boundary, at 100,000 astronomical units, or 1.6 light-years, represents the practical edge of the Sun's gravitational dominance, where stellar perturbations become significant. Beyond this distance, objects are no longer gravitationally bound to the Sunday. The Sun contains 99.86% of the Solar System's total mass, 1.989 times 10 to the 30th kilograms, with the remaining 0.14% distributed among planets, moons, asteroids, comets, and interplanetary medium. Jupiter alone comprises 2/3 of the non-solar mass at 318 Earth masses, while all other planets combined total roughly 1/3. This extreme mass concentration means the solar system's center of mass, of the barycenter, lies just outside the Sun's surface when Jupiter and Sun are aligned, and within the Sun when Jupiter is at quadrature. The Sun's gravity dominates out to roughly 2 light-years beyond the Oort cloud, where its Hill sphere, the region where its gravity exceeds the tidal force from the Milky Way and neighbouring stars, ends. Within this sphere, objects can maintain stable orbits. Beyond it, galactic and stellar perturbations dominate. Light travel times illustrate the solar system's scale. Sunlight reaches Earth in 8 minutes 20 seconds. Mars at 1.5 astronomical units receives sunlight in 12 to 13 minutes depending on orbital positions. Jupiter at 5.2 astronomical units is 43 light minutes away. Saturn at 9.5 astronomical units is 80 light minutes. Neptune at 30 astronomical units is 4.1. Light hours distant signals from Neptune take over 4 hours to reach Earth, making real-time communication impossible. Pluto at 39 astronomical units is 5.5 light hours away. Commands sent to New Horizons during its Pluto flyby took 4.5 hours to arrive, with confirmation returning another 4.5 hours later, a 9-hour round-trip communication delay. Voyager 1 at 161 astronomical units experiences a 22-hour round-trip light travel time, constraining mission operations to pre-planned commands rather than interactive control. Our cosmic address situates Earth in a hierarchy of increasingly larger structures. Earth orbits the Sun, one star among hundreds of billions in the Milky Way galaxy. The Sun resides in the Orion Arm, a minor spiral arm approximately 10,000 light-years long. The Orion Arm lies between two major spiral arms, the Perseus Arm inward and the Sagittarius Arm toward the galactic center. The Sun orbits the galactic center at a distance of 26,000 light-years, completing one galactic year, one full orbit every 225 million years. The solar system has completed roughly 20 galactic orbits since its formation 4.6 billion years ago. During this time, Earth has circled the galaxy 20 times, passing through spiral arms, regions of intense star formation, and the relative quiet of inter-arm space. Our location currently places us in a relatively calm region, midway between spiral arms, contributing to Earth's long-term habitability by avoiding excessive radiation from nearby supernovae and stellar encounters that might perturb the Oort cloud, sending comets into the inner solar system. The solar system's motion through space is complex, involving multiple components. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at 220 kilometers per second, carrying the solar system along. But the Sun also moves, relative to nearby stars, its peculiar velocity at roughly 13.4 kilometers per second toward a point called the solar apex, located near the constellation Hercules at coordinates right ascension 18 hours, declination plus 30 degrees. This motion results from the Sun's birth location and the gravitational influences encountered during its 4.6 billion year journey around the galaxy. Additionally, the Milky Way moves through space at 600 kilometers per second relative to the cosmic microwave background, heading toward the Great Attractor and Shapley supercluster, large-scale structures hundreds of millions of light-years away. These nested motions mean Earth moves through space at hundreds of kilometers per second depending on the reference frame, never occupying the same position twice in its journey through the cosmos. Nearest stars and the local bubble. Proxima Centauri, the Sun's nearest stellar neighbour, lies 4.244 light-years away, 40.2 trillion kilometres, or 268,770 astronomical units. This red dwarf star, with mass 0.12 solar masses and spectral type M5, orbits the binary system Alpha Centauri A and B in a wide elliptical orbit, taking roughly 550,000 years to complete. Proxima was discovered in 1915 by Robert Innes. Through its large proper motion, the angular change in position against background stars amounting to 3.85 arcseconds per year. Despite being our closest stellar neighbour, Proxima is invisible to the naked eye at apparent magnitude 11.1, requiring telescopes to observe. The star's proximity makes it the prime target for interstellar mission concepts. Breakthrough Starshot proposes sending light sail spacecraft accelerated by ground-based lasers to 20% light speed, reaching Proxima in approximately 20 years. Discovery of Proxima Centauri b in 2016, an Earth-mass planet orbiting in the habitable zone, increased interest in exploring this system. Alpha Centauri A and B, a binary pair orbiting their common center of mass every 79.9 years, lie 4.37 light-years away, only slightly farther than Proxima. Alpha Centauri A is a G2V star, nearly identical to the Sun, with mass 1.1 solar masses, while Alpha Centauri b is a K1V orange dwarf with mass 0.9 solar masses. The star's separation varies from 11 to 36 astronomical units as they follow their elliptical orbits. Combined apparent magnitude reaches minus 0.27, making Alpha Centauri the third brightest star system in Earth's night sky after Sirius and Canopus. The system's proximity and Sun-like primary make it a natural target for searching for habitable planets. Despite extensive searches, confirmed planets remain elusive in the Alpha Centauri AB system, though candidate signals continue to be investigated. The system's location in the southern constellation Centaurus makes it invisible from most northern latitudes, observable only from locations below 29 degrees north latitude. Barnard's star, located 5.96 light-years away in the constellation Ophiuchus, holds the record for the largest proper motion of any star 3 arcseconds per year. This M4 red dwarf, with mass 0.16 solar masses, moves rapidly across the sky due to its proximity and velocity relative to the Sun, approximately 140 kilometers per second. Discovered by E.E. Barnard in 1916 through its high proper motion, the star approaches the Sun and will reach its closest distance of 3.8 light-years in approximately 10,000 years before receding. Historical claims of planets orbiting Barnard's star, announced in the 1,960 seconds based on astrometric wobbles, were later disproven. However, a confirmed planet, Barnard's star B, was announced in 2018, a super-Earth with minimum mass 3.2 times Earth's mass, orbiting at 0.4 astronomical units with a 233-day period. At such distance, the planet receives little stellar heating and likely has surface temperatures around 170 Kelvin, making it a frozen world. Sirius, the brightest star in Earth's night sky, with apparent magnitude -1.46, lies 8.6 light-years away in the constellation Canis Major. Sirius A, the primary star, is an A1V white main sequence star with mass 2.02 solar masses and luminosity 25 times the Sun's. The star's brightness results from both intrinsic luminosity and proximity. Sirius B, discovered in 1862 by Alvan Graham Clark through its gravitational influence on Sirius A, is a white dwarf, the first ever discovered with mass 0.98 solar masses, compressed into a radius similar to Earth's. The white dwarf orbits Sirius A every 50.1 years at separations ranging from 8 to 32 astronomical units. Sirius B represents the endpoint of stellar evolution for stars, between roughly 1 and 8 solar masses, having exhausted its nuclear fuel and shed its outer layers approximately 120 million years ago. The system's age is estimated at 240 million years, making both stars relatively young. Ancient Greek observers described Sirius as red rather than the blue-white colour seen today, possibly indicating Sirius B was a red giant during historical times, though this interpretation remains controversial. Epsilon Eridani, located 10.5 light-years away in the constellation Eridanus, is a K2V orange dwarf with mass 0.82 solar masses and age approximately 800 million years. The star gained prominence as one of the first targets of SETI observations Project Ozma in 1960, searched for radio signals from Epsilon, Eridani and Tau Ceti. Infrared observations revealed a debris disk surrounding the star, indicating a planetary system in formation or recent planet formation. At least one confirmed planet, Epsilon Eridani b, orbits the star with mass roughly 0.78 Jupiter masses at 3.5 astronomical units, comparable to the asteroid belt's location in our solar system. The planet's orbit is highly eccentric, with eccentricity 0.7, taking 7.4 years to complete. Additional planet candidates have been proposed based on disk structure and astrometric measurements, though confirmation remains pending. The system's youth and proximity make it valuable for studying planetary system evolution and debris disk dynamics. The local bubble, also called the local cavity, is a region of hot, low-density interstellar gas, extending roughly 300 light-years in most directions from the Sunday. This cavity in the interstellar medium contains gas heated to approximately 1 million Kelvin, but at extremely low density, 0.001 atoms per cubic centimeter, compared to typical interstellar densities of 1 atom per cubic centimeter. The bubble's hot, diffuse gas emits soft X-rays detectable by space-based observatories. The local bubble formed through supernova explosions over the past 10 to 20 million years, with approximately 15 to 20 supernovae occurring within the region, heating and dispersing gas. The expanding supernova remnants merged, creating the cavity. The Sun entered the local bubble roughly 5 to 10 million years ago, having previously resided in denser interstellar regions. The bubble's low density reduces interstellar absorption of starlight, enabling clearer views of distant stars and galaxies. The boundary between the local bubble and surrounding denser gas shows complex structure with filaments, shells, and cavities created by stellar winds and supernovae. Stellar density in the solar neighborhood averages approximately 0.14 stars per cubic light-year when counting all stellar systems within 20 light-years. This figure includes single stars, binary pairs, and multiple star systems, counting each system as one unit. Including brown dwarf substellar objects below the hydrogen fusion limit increases the count slightly. The nearest 100 stellar systems within roughly 20 light-years include approximately 130 individual stars and brown dwarfs. As many systems are multiples. Most nearby stars are red dwarfs, M-type stars, with masses 0.08 to 0.5 solar masses, comprising roughly 75% of stellar populations. The nearest few dozen stars include only a handful of Sun-like G-type stars and more massive stars, reflecting the fact that massive stars are intrinsically rare. Stellar density increases toward the galactic plane. We reside approximately 50 light-years above the plane and increases dramatically toward the galactic center, where densities reach thousands of stars per cubic light-year in. The central bulge. The Sun's motion relative to nearby stars carries the solar system at 13.4 kilometers per second toward the solar apex. A point in the sky near coordinates right ascension, 18 hours 28 minutes. Declination plus 30 degrees. Located in the constellation Hercules near the border with Lyra. This motion is measured relative to the local standard of rest, the average velocity of stars in the solar neighborhood orbiting the galactic center. The Sun's peculiar velocity, its deviation from circular galactic rotation, has three components: 11 kilometers per second toward the galactic center, 12 kilometers per second in the direction of galactic rotation, and 7 kilometers per second perpendicular to the galactic plane, moving northward. These velocities result from the Sun's birth environment and gravitational interactions during its 4.6 billion-year galactic journey. Over hundreds of thousands of years, the Sun's motion changes the configurations of nearby stars and constellations. In 50,000 years, the brightest stars will have noticeably shifted positions, rendering current constellations unrecognizable, open clusters and stellar neighborhoods. The Hyades, the nearest open star cluster to Earth at 153 light-years distance, contains approximately 400 member stars spread across roughly 60 light-years in the constellation Taurus. The cluster's age is 625 million years. Determined from stellar evolution models comparing observed stellar types with theoretical isochrones, curves representing stellar populations of specific ages on color magnitude diagrams. The Hyades proximity makes it a fundamental distance calibrator, measuring distances to individual member stars through parallax, establishes the cluster's distance precisely, which then calibrates other distance determination methods. The cluster's brightest stars, Aldebaran excepted, form a V-shape in Taurus, marking the bull's face. Aldebaran, the bright orange giant at magnitude 0.85, appears in the same direction but lies only 65 light-years away, a foreground star not physically associated with the cluster. The Hyades moves through space at 45 kilometers per second toward a convergent point in the constellation Orion, meaning cluster members appear to converge toward a specific direction due to perspective paralleling railroad tracks appearing to converge at the horizon. The Pleiades, also called the Seven Sisters, or M45, lies 444 light-years away in Taurus and contains approximately 1,000 confirmed member stars, though only 6 or 7 are easily visible to the naked eye. The cluster's age is approximately 100 million years, significantly younger than the Hyades, still showing bright blue B-type main sequence stars that evolve quickly. The Pleiades' most massive stars will exhaust their core hydrogen within another 100 million years, becoming red giants. The cluster is famous for its reflection nebulae, clouds of interstellar dust illuminated by starlight from the bright cluster members, particularly Merope, whose surrounding nebulosity was discovered photographically in 1885. The nebula is not a remnant of the molecular cloud from which the cluster formed. That cloud dissipated tens of millions of years ago, but rather a chance encounter with interstellar dust through which the cluster is currently passing. The Pleiades' brightness and distinctive appearance made it culturally significant across human civilizations, featuring in myths, calendars, and navigation from ancient times. The Beehive cluster, designated M44 or Praesepe, lies 577 light-years away in Cancer and contains over 1,000 stars within a volume roughly 20 light-years across. The cluster's age is estimated at 600 million years, similar to the Hyades, and likely formed from the same giant molecular cloud complex. The Beehive is visible to the naked eye as a fuzzy patch of magnitude 3.1, making it one of few open clusters easily seen without optical aid. Galileo resolved the cluster into stars using his telescope in 1609, counting 36 stars, one of astronomy's first telescope observations. Modern surveys identify over 1,000 members, including numerous red dwarfs and white dwarfs. The cluster's relatively advanced age means the most massive stars have already evolved off the main sequence, leaving behind white dwarfs, stellar remnants, providing clues about stellar evolution timescales. Exoplanet searches have discovered planets orbiting Beehive members, indicating planet formation occurs successfully in cluster environments despite gravitational perturbations from neighbouring stars. Coma Berenices, located 280 light-years away, is an open cluster containing 37 confirmed member stars spread across roughly 20 light-years. This cluster is nearby and sparse, making membership determination challenging. Distinguishing true cluster members from field stars along the same line of sight requires precise measurements of positions, proper motions, and radial velocities. The MEL 111 designation Melot 111 refers to this cluster catalogued by Philibert Jacques Melot in 1915. The cluster's age is approximately 450 million years. Unlike denser clusters where stars remain gravitationally bound for hundreds of millions of years, Coma Berenices is loosely bound and likely dispersing stars gradually drifting apart through encounters with molecular clouds and differential galactic rotation. In another few 100 million years, former cluster members will be scattered across hundreds of light years, becoming indistinguishable from field stars, except through detailed kinematic analysis, revealing their common origin and motion through space. Open clusters are young stellar populations containing 100 to 10,000 members formed from the same giant molecular cloud, sharing common ages, chemical compositions, and initial motions. They populate the galactic disk, particularly spiral arms where ongoing star formation occurs. Open clusters contrast with globular clusters, ancient spherical collections of hundreds of thousands to millions of stars inhabiting the galactic halo. Open clusters form when molecular clouds, cold, dense regions of hydrogen gas, with temperatures around 10 to 50 Kelvin, undergo gravitational collapse, triggered by shocks from supernova blast waves, spiral density waves, or cloud collisions. The collapsing cloud fragments into hundreds to thousands of cores, each forming a star. The resulting cluster remains gravitationally bound for some time, but most open clusters are loosely bound and disperse over tens to hundreds of millions of years. Only the densest open clusters survive billions of years. The oldest known open cluster, NGC 188, is approximately 7 billion years old, but remains exceptionally rare among open clusters. Lifetimes of open clusters range from 100 million years for loosely bound associations to several billion years for dense, compact clusters. Dispersal occurs through multiple mechanisms. Differential galactic rotation stars at different galactic radii orbit at different velocities gradually shears clusters apart. Encounters with giant molecular clouds, massive, dense regions containing 100,000 to 10 million solar masses, gravitationally perturb cluster members, ejecting some and loosening others. Two-body relaxation, gravitational encounters between cluster members exchanging energy gradually evaporates the cluster as some stars gain energy exceeding escape velocity. The rate of dispersal depends on stellar density, total mass, and galactic environment. Dense clusters in interarm regions survive longer than loose clusters in spiral arms where molecular cloud encounters are frequent. Approximately 90% of open clusters disperse within 1 billion years, releasing their stars into the general galactic disk population. Formation of open clusters begins with giant molecular clouds, the largest gravitationally bound structures in galaxies containing 10,000 to 10 million solar masses of gas, primarily molecular hydrogen. Within these clouds, smaller, dense cores with masses 100 to 10,000 solar masses become gravitationally unstable and collapse. Collapse proceeds hierarchically. The cloud fragments into clumps, clumps fragment into cores, and cores form individual stars or binary systems. Star formation efficiency, the fraction of gas mass converted to stars, is only 1 to 10% in most regions. Massive stars forming in the cluster's densest regions ignite fusion first, emitting intense ultraviolet radiation that ionizes surrounding gas, creating HII regions glowing nebulae like the Orion Nebula. This radiation pressure and stellar winds from massive stars gradually disperse remaining gas, terminating star formation after a few million years. The emerging cluster initially remains embedded in natal gas, becoming visible only after gas disperses. The Orion Nebula cluster represents this stage, a young cluster, approximately 1 million years old, still embedded in its molecular cloud, with star formation ongoing in surrounding dense cores. Approximately 1,100 open clusters have been catalogued in the Milky Way, though the true population likely exceeds 100,000 when including small associations and clusters obscured by interstellar dust. Most catalogued clusters lie within 15,000 light-years of the Sun relatively nearby, because dust extinction limits visibility of distant clusters. Surveys using infrared astronomy penetrate dust more effectively, revealing numerous previously hidden clusters. The distribution of open clusters traces the galactic disk and spiral arm structure. Young clusters with ages below 10 million years concentrate in spiral arms, marking regions of recent star formation. Older clusters with ages 100 million to 1 billion years are more dispersed, having drifted from their formation sites through differential galactic rotation. The oldest open clusters, exceeding 1 billion years, are rare and scattered throughout the disk. Some, like NGC 188 at 7 billion years, rival globular cluster ages, but remain in the disk, with metal-rich compositions indicating recent formation from enriched gas. Unlike ancient metal-poor globular clusters formed when the galaxy was young, the Orion arm and spiral structure. The Orion Cygnus arm, also called the Orion spur or local arm, is a minor spiral arm approximately 10,000 light-years long and 3,500 light-years wide, extending between two major spiral arms of the Milky Way. The Sun and Solar System reside within this arm, positioned roughly midway between the Perseus arm, the next major arm inward toward the galactic center, and the Sagittarius arm, the next major arm outward. The Orion Arm's designation as a minor or spur arm indicates it connects between major arms rather than wrapping completely around the galaxy, like the Perseus, Sagittarius, Scutum Centaurus, and Norma arms. However, recent studies using more precise distance measurements to young star-forming regions suggest the Orion Arm may be more substantial than previously thought, possibly representing a significant feature rather than a mere connection. The arm contains numerous star-forming nebulae, including the Orion Nebula, Eagle Nebula, North America Nebula, and Rosette Nebula regions, where massive stars are being born from collapsing molecular clouds. The Sun's location places it 26,000 light-years from the galactic center, approximately halfway between center and edge along the galactic radius. More precisely, measurements using the orbit of the star S2 around the central supermassive black hole Sagittarius A star yield a distance of 26,670 light-years, with uncertainty around 300 light-years. This distance is determined through multiple methods, including red clump giant stars, stars at a specific evolutionary stage with known intrinsic brightness and masers, naturally occurring microwave lasers in star-forming regions whose positions can be measured precisely using very long baseline interferometry. The Sun resides approximately 50 light-years above the galactic midplane, oscillating perpendicular to the disk with a period of roughly 60 million years. This oscillation carries the solar system through the midplane every 30 million years. Some researchers have proposed correlations between midplane crossings and mass extinctions on Earth, hypothesizing that increased comet impacts occur when passing through the disk's denser regions, though evidence remains debated. Galactic rotation carries the Sun and solar system around the galactic center at approximately 220 kilometers per second, about 490,000 miles per hour. This velocity maintains the Sun's roughly circular orbit, balancing gravitational attraction from the galaxy's mass distribution. The orbital period, 1 galactic year, or cosmic year, is approximately 225 million years. During Earth's 4.6 billion year history, the solar system has completed roughly 20 galactic orbits. The last time Earth occupied its current position in the galaxy, dinosaurs had not yet appeared. Small reptiles were diversifying in the Triassic period, 225 million years ago. 1 galactic year before that, 450 million years ago, life was just colonizing land during the Ordovician period. Galactic rotation is differential. Inner regions orbit faster than outer regions, unlike solid body rotation, where all parts take the same time to complete one revolution. This differential rotation arises because most galactic mass concentrates centrally rather than being uniformly distributed. The rotation curve velocity versus radius remains nearly flat beyond a few thousand light-years, indicating the presence of dark matter extending far beyond the visible disk. The Perseus arm, a major spiral arm located inward from the Orion arm, lies approximately 6,500 light-years closer to the galactic center. The arm contains numerous massive star-forming regions, young star clusters, and HII regions, ionized hydrogen nebulae surrounding hot young stars. The Perseus molecular cloud complex, one of the galaxy's most active star-forming regions, contains clumps with masses exceeding 100,000 solar masses, forming high-mass stars. The California Nebula, visible in the northern sky, belongs to the Perseus arm. Spiral arms are regions of enhanced stellar density, roughly twice the background density where stars, gas, and dust concentrate. But individual stars do not remain permanently in spiral arms. Instead, stars orbit the galactic center at velocities determined by their radius, occasionally passing through spiral arms. Spiral arms represent density waves, gravitational perturbations that compress gas as it passes through, triggering star formation. The bright young stars that form light up the arms before the stars drift away, while the arms themselves persist as quasi-permanent features of the galactic gravitational potential. The Sagittarius arm, a major spiral arm lying outward from the Orion arm, is approximately 6,500 light-years more distant from the galactic center than the Sunday. The arm contains prominent star-forming regions, including the Lagoon Nebula M8, Omega Nebula M17, and Eagle Nebula M16, the latter famous for the Hubble Space Telescope's Pillars of Creation image, showing towers of gas and dust where stars are forming. The Sagittarius arm curves through the southern Milky Way as seen from Earth, visible on summer nights in the northern hemisphere when Sagittarius constellation marking the direction toward the galactic center is highest in the sky. The arm's name derives from this constellation. Beyond the Sagittarius arm lies the Scutum Centaurus arm, and then the Norma arm, the outermost major spiral arms, before reaching the galaxy's edge, where stellar density drops precipitously. These outer arms are difficult to observe from the Sun's location, due to intervening dust and the challenges of measuring distances to remote objects. Star-forming regions populate the Orion arm and other spiral arms, marking sites where molecular clouds collapse to form new stars. The Orion Nebula, M42, located approximately 1,340 light-years away, is the nearest massive star-forming region and the most studied. The nebula hosts the Trapezium cluster, a young open cluster with 4 bright O-type stars ionizing surrounding gas and illuminating the nebula through reflected and re-emitted light. The Carina Nebula, located approximately 7,500 light-years away, contains Eta Carinae, a massive, luminous blue variable star that underwent a giant eruption in the 1,840 seconds, ejecting several solar masses. The Eagle Nebula, approximately 7,000 light-years distant, contains evaporating gaseous globules, dense clouds of gas resisting ionization by nearby massive stars, and protostellar disks observable in infrared wavelengths. These nebulae mark the locations of recent star formation, tracing spiral arm structure through the young massive stars they contain. Spiral arm structure arises from density wave theory, proposed by C. Lin and Frank Hsu in the 1960 seconds, explaining spiral patterns as gravitational waves propagating through the galactic disk. These waves create regions of enhanced density where stars and gas accumulate, similar to traffic jams on highways. Cars slow down and bunch together in the jam, even though individual cars pass through. Molecular clouds entering spiral arms are compressed by the density wave, triggering gravitational collapse and star formation. Massive stars that form have lifetimes only 10 to 100 million years, much shorter than the time to orbit the galaxy, so they evolve and die while still near their birthplaces in spiral arms, creating the bright blue appearance of spiral arms in disk galaxies. Lower mass stars like the Sun, with lifetimes exceeding 10 billion years, complete many galactic orbits and thus populate the disk uniformly rather than concentrating in arms. The spiral pattern persists because the density wave pattern rotates rigidly. All parts of the spiral take the same time to complete one revolution, with pattern speed approximately half the stellar rotation speed in the mid-disk regions. The pitch angle of the Milky Way's spiral arms, the angle between the spiral arm and a circle centered on the galactic center, is approximately 12 degrees, indicating relatively tightly wound spirals. This is measured by mapping the locations of young star clusters, HII regions, and masers sources whose distances can be determined accurately and fitting logarithmic spiral patterns to their distributions. The Milky Way is classified as a barred spiral galaxy of type SBBC, where SB denotes a barred spiral. The first B indicates moderately tightly wound arms, and the second C indicates moderate central concentration. The bar, an elongated structure extending roughly 27,000 light-years from the center and rotating with a period approximately 200 million years, drives spiral arm formation through gravitational perturbations. Gas flowing along the bar accumulates at the bar's ends, where spiral arms begin, feeding star formation. The relationship between bars and spiral structure remains an active research area, with simulations suggesting bars are quasi-permanent features that form, dissolve, and reform during galactic evolution. Globular clusters, halo objects. M13, also called the Great Globular Cluster in Hercules, lies approximately 25,000 light-years away and contains roughly 300,000 stars packed into a sphere roughly 145 light-years in diameter. At the cluster's core, stellar density reaches several hundred stars per cubic light-year, compared to 0.14 stars per cubic light-year in the solar neighborhood. M13's age is estimated at 11.6 billion years, based on stellar population models fitting the main sequence turn-off point, the luminosity where stars are just exhausting their core hydrogen and evolving to red giants. This age indicates the cluster formed during the early galaxy's assembly. M13 was discovered by Edmund Halley in 1714 and catalogued by Charles Messier in 1764. William Herschel first resolved it into individual stars in 1782. In 1974, M13 was targeted by the Arecibo message, a radio transmission encoding information about humanity and Earth sent toward the cluster. The message will reach M13 in approximately 25,000 years, with any reply taking another 25,000 years to return. Omega Centauri, designated NGC 5139, is the largest and most massive globular cluster orbiting the Milky Way. Located 15,800 light-years away in the constellation Centaurus, visible only from southern latitudes, Omega Centauri contains approximately 10 million stars with total mass around 4 million solar masses. The cluster spans 150 light-years in diameter with a dense core extending 15 light-years. Omega Centauri's unusual properties, including multiple stellar populations with different ages and metallicities, suggest it might be the stripped core of a dwarf galaxy captured and tidally disrupted by the Milky Way billions of years ago. Evidence includes a central black hole with mass approximately 40,000 solar masses detected through stellar velocity dispersions, the spread of stellar velocities indicating a concentrated central mass. The cluster's stars show chemical abundance variations indicating multiple formation episodes, unlike typical globular clusters with uniform compositions. Omega Centauri is visible to the naked eye at magnitude 3.9, appearing as a fuzzy star. It was catalogued by Ptolemy in 150 AD as a star, recognized as a cluster only in the 1,670 seconds. 47 Tucanae, designated NGC 104, is the second brightest globular cluster after Omega Centauri. Located 13,000 light-years away, near the Small Magellanic Cloud, appearing nearby on the sky, but much closer in space, 47 Tucanae contains approximately 1 million stars within 120 light-years. The cluster's dense core, extending only 1.2 light-years radius, contains over 100,000 stars, with densities exceeding 10,000 stars per cubic light-year. At such densities, stellar encounters occur frequently, affecting stellar evolution. Blue stragglers stars, appearing younger and more massive than possible, given the cluster's age, likely form through stellar collisions and mergers in the dense core. 47 Tucanae contains over 20 millisecond pulsars, rapidly rotating neutron stars spun up through mass accretion from binary companions more than any other globular cluster. The cluster also hosts numerous X-ray binaries, where neutron stars or black holes accrete matter from companion stars, emitting X-rays. These compact objects formed from the most massive stars born in the cluster, which have long since evolved off the main sequence and exploded as supernovae. Approximately 157 globular clusters are known to orbit the Milky Way, though the total population likely approaches 200 when accounting for clusters hidden behind the galactic disk and undiscovered clusters at great distances. The number is small compared to giant elliptical galaxies like M87, which hosts over 12,000 globular clusters. The globular cluster population provides clues about galactic formation history. Clusters divide into metal-poor and metal-rich populations, the metal-poor clusters, with iron abundances below 1% solar, formed during the galaxy's initial collapse 12 to 13 billion years ago. Metal-rich clusters with iron abundances 10 to 100% solar formed later after the galaxy's disk assembled and enriched with metals from supernovae. The metal-poor clusters orbit in the halo with high-velocity dispersions and eccentric orbits, while metal-rich clusters concentrate toward the galactic disk with more circular orbits. This dichotomy reflects formation epochs. Halo clusters formed in small protogalactic fragments that merged to build the galaxy, while disk clusters formed from enriched gas after the disk settled. Halo distribution of globular clusters forms a roughly spherical envelope extending 100,000 light-years or more from the galactic center, far beyond the disk's 50,000 light-year radius. The halo contains old metal-poor stars and globular clusters orbiting with high velocities on elongated elliptical orbits, inclined at random angles to the disk plane. This contrasts sharply with the disk's orderly rotation in a thin plane. The halo's properties suggest it formed through the merger of smaller protogalactic fragments during the galaxy's early history. Each fragment contributed its stellar content to the growing halo, while gas settled into the rotating disk. This scenario, proposed by Leonard Searle and Robert Zinn in 1978, is supported by chemodynamical simulations showing that hierarchical galaxy formation naturally produces extended stellar halos. The Gaia spacecraft's precise measurements of stellar motions in the halo revealed multiple stellar streams, elongated groups of stars sharing common motions interpreted as debris from disrupted dwarf galaxies and globular clusters, confirming the merger origin of the halo. Population 2 stars, defined by Walter Bade in 1944, are metal-poor stars with iron abundances below 10% solar value, often written as metallicity Fe H, less than -1. These stars formed from gas enriched only by the first generation of massive stars, population 3 stars that formed from primordial hydrogen and helium and exploded as supernovae, dispersing the first heavy elements. Globular clusters contain predominantly population 2 stars, reflecting formation from minimally enriched gas during the galaxy's first billion years. The oldest population 2 stars observed have ages matching the universe's age, 13.8 billion years, confirming they formed shortly after the Big Bang. Their low metallicity affects stellar structure. Metal-poor stars are hotter and bluer at given mass compared to metal-rich population I stars populating the disk. This is because metals increase opacity resistance to radiation flow in stellar atmospheres, causing metal-rich stars to be larger and cooler at fixed luminosity. Population II stars' kinematics, high-velocity dispersions, and elongated orbits distinguish them from population D stars' orderly circular disk orbits. Tidal streams result when globular clusters and dwarf galaxies pass through the Milky Way's gravitational field, experiencing tidal forces differential gravity that stretch and disrupt them. Stars stripped from these objects form elongated streams orbiting the galaxy. Palomar 5, a sparse globular cluster 75,000 light-years away, exhibits prominent tidal tails extending 13,000 light-years on either side. Discovered through wide-field surveys mapping stellar positions and motions, these tails formed as the cluster repeatedly passed through the galactic disk, with each passage stripping stars through tidal forces. Simulations predict Palomar 5 will completely dissolve within 1 billion years, its stars dispersing into the halo. The Sagittarius stream, discovered in the 1,990 seconds, encircles the galaxy, a trail of stars from the Sagittarius dwarf elliptical galaxy being tidally disrupted by the Milky Way. The stream wraps multiple times around the galaxy, indicating the dwarf has orbited several times while shedding stars. These streams provide evidence of ongoing galactic cannibalism, the Milky Way growing through accretion and disruption of smaller systems. Ages of globular clusters range from 11.5 to 13 billion years, determined through stellar population modelling comparing observed colour magnitude diagrams with theoretical isochrones. The oldest clusters are among the universe's oldest objects, forming shortly after the first galaxies assembled. The age spread of several 100 million years among clusters suggests formation extended over the galaxy's first billion years rather than occurring simultaneously. Metal-poor halo clusters tend to be older, while metal-rich disk clusters are younger, consistent with two-phase formation. Initial halo assembly followed by disk formation from enriched gas. Some globular clusters may be younger, NGC 1,850 inches. The Large Magellanic Cloud, often called a globular cluster, is only 100 million years old and resembles a dense open cluster. The distinction blurs for young clusters, depending on whether mass and density or age define classification. Globular clusters provide unique laboratories for stellar evolution studies containing coeval populations, simplifies comparisons, as all stars formed simultaneously and differ only in initial mass. The Milky Way disk and bulge. The Milky Way disk extends approximately 100,000 to 180,000 light-years in diameter, depending on measurement, method, and definition. Traditional estimates based on stellar density profiles yielded diameters around 100,000 light-years. Recent studies using Gaia spacecraft astrometry and surveys mapping red giant stars and other traces find evidence for stellar populations extending to 180,000 light-years, nearly doubling previous estimates. The disk is not sharply bounded but fades gradually, making precise diameter determination dependent on the sensitivity threshold chosen. The disk divides into thin and thick components with distinct properties. The thin disk, extending 1,000 light-years above and below the midplane, contains young star-forming regions, open clusters, OB associations, and gas. The thick disk, extending 3,000 light-years, contains older metal-poor stars formed 10 to 12 billion years ago during the galaxy's early history. The disk's thin vertical extent, compared to its broad radial span, creates the flattened spiral galaxy shape visible in edge-on galaxies like NGC 891. Stellar population estimates for the Milky Way range from 200 to 400 billion stars, with uncertainty arising from the difficulty counting faint, low-mass stars comprising most of the population. Red dwarfs M-type stars with masses 0.08 to 0.5 solar masses outnumber Sun-like stars by factors of 10 to 1. White dwarfs, stellar remnants from stars that exhausted their nuclear fuel, add another population, comparable in number to living stars but contributing minimal luminosity. Brown dwarfs substellar objects below the hydrogen fusion mass limit of 0.08 solar masses may outnumber stars, though detection remains challenging for the coolest examples. Star counts are performed using surveys like Gaia, measuring parallaxes and motions. For nearly 2 billion stars, still only 1% of the total, and extrapolating using stellar mass functions and density profiles. The stellar mass totals approximately 60 billion solar masses, with the remainder of the galaxy's 5 trillion solar mass distributed between gas, dust, and dark matter. The bulge, the central concentration of stars surrounding the galactic center, extends approximately 10,000 light-years radius, forming a boxy or peanut-shaped structure in 3 dimensions. This shape results from vertical buckling instabilities in the central bar. Gravitational interactions cause stars in the bar to gain vertical motion, creating the observed peanut shape when viewed edge-on. Infrared observations penetrating dust reveal the bulge's true structure, dominated by old, metal-rich stars aged 10 billion years. The bulge contains approximately 20 billion stars, with total mass around 20 billion solar masses. Star formation in the bulge ceased billions of years ago, when gas was consumed or expelled, explaining the absence of young blue stars and molecular clouds. The bulge's chemical composition shows enrichment ion abundances reach solar values indicating rapid early star formation that processed gas through multiple stellar generations before formation ceased. Nuclear star clusters, extremely dense stellar concentrations within 10 light-years of the galactic center orbit. Sagittarius A star, the central black hole, with velocities exceeding 1,000 kilometers per second. The central bar, discovered through infrared surveys in the 1,990 seconds, extends approximately 27,000 light-years from end to end and rotates with period roughly 200 million years, faster than the disk's 225 million year rotation period. The bar's pattern speed, the angular velocity at which the bar rotates, is roughly twice the disk's angular velocity at the Sun's radius, placing the Sun outside the bar's corrotation radius, where stellar orbits synchronize with the bar. Inside corrotation, stars orbit faster than the bar pattern, while outside corrotation, stars orbit slower. The bar influences galactic dynamics by channeling gas inward along spiral arms that begin at the bar's ends, feeding star formation in the central kiloparsecs. Bars are common in disk galaxies. Roughly 2/3 show barred structure forming through gravitational instabilities when disk mass and rotation support bar modes. Bars evolve over time, growing through accretion and angular momentum transfer to the outer disk, then potentially dissolving and reforming, creating complex evolutionary cycles. Sagittarius A star, the radio source marking the galactic center, contains a supermassive black hole with mass 4.15 million solar masses determined through tracking stellar orbits around the central point mass. The star S2, with orbital period 16 years, approaches within 17 light-hours, roughly 4 times Pluto's distance from the Sun, reaching velocities 3% light speed at periapse. General relativistic effects, including gravitational redshift and orbital precession, are detectable in S2's orbit, confirming Einstein's theory in the strong field regime. The black hole itself is inactive, accreting minimally roughly 10 to the -7th solar masses per year, producing little radiation. Occasional flares in X-rays and infrared indicate sporadic accretion events, perhaps from asteroids or gas clouds falling in. The Event Horizon Telescope imaged Sagittarius A star in 2022, resolving the black hole's shadow, the dark region where photon orbits are gravitationally captured, surrounded by a bright ring of emission from hot gas orbiting near the event horizon. The image confirmed the black hole's mass and spin, showing structure varying on timescales of minutes due to turbulent accretion flows. Total mass of the Milky Way, including dark matter, is approximately 1.5 trillion solar masses within 200,000 light-years radius based on satellite galaxy motions, stellar streams, kinematics, and rotation curve modeling. Luminous matter stars, gas dust comprises only 10%, or roughly 150 billion solar masses. Dark matter dominates, forming an extended spherical halo reaching beyond the visible disk. The dark matter density profile decreases with radius, but the total enclosed mass increases because volume grows as radius cubed. Measuring total mass requires tracing dynamics to large radii where dark matter dominates. Satellite galaxies orbiting the Milky Way at distances 100,000 to 500,000 light-years provide kinematic tracers. Applying the virial theorem relating kinetic and potential energy for bound systems to satellite velocities yields the enclosed mass. The Milky Way's mass places it among the more massive spiral galaxies, comparable to Andromeda's 1.5 trillion solar masses and exceeding typical spiral masses of 500 billion solar masses. Gas content in the Milky Way totals 10 to 15 billion solar masses, distributed primarily as molecular hydrogen in molecular clouds, atomic hydrogen in the diffuse interstellar medium, and ionized hydrogen in HII regions and hot gas. Molecular hydrogen, existing in dense cold clouds with temperatures 10 to 50 Kelvin, comprises roughly half the gas mass. These clouds, traced by carbon monoxide emission CO molecules, emit rotational lines serving as H2 proxies. Since H2 lacks strong emission lines, concentrate in spiral arms and the central kiloparsecs, where star formation occurs. Atomic hydrogen, traced through 21 centimeter hyperfine transition line emission, forms an extended disk reaching 50,000 light-years radius. The atomic hydrogen layer is thicker than stellar and molecular disks extending thousands of light-years vertically. Ionized hydrogen exists in HII regions surrounding massive stars and in a hot diffuse component with temperature 1 million Kelvin permeating the disk and halo. This hot gas, heated by supernova shocks, occupies large volumes but contributes minimal mass. The Milky Way's gas fraction gas mass divided by total baryonic mass is roughly 10% lower than many spiral galaxies, reflecting ongoing star formation consuming gas over billions of years. Satellite galaxies, the local group edge, the Large Magellanic Cloud, abbreviated LMC, is a satellite galaxy orbiting the Milky Way at approximately 160,000 light-years distance. With total mass around 10 billion solar masses and containing roughly 10 billion stars, the LMC is classified as a Magellanic spiral, an irregular galaxy showing some spiral structure. The LMC is visible to the naked eye from southern latitudes as a faint cloud spanning 10 degrees 20 moon diameters across the sky. It was known to indigenous cultures in the southern hemisphere for millennia and described by Persian astronomer al-Sufi in 964 AD. Ferdinand Magellan's expedition made it widely known to European astronomy, hence the name. The LMC hosts active star formation with numerous HII regions, young star clusters, and stellar nurseries. The Tarantula Nebula, also called 30 Doradus, is the LMC's largest star-forming region and the most active in the local group, containing the massive star cluster R136 with numerous stars exceeding 100 solar masses. The Small Magellanic Cloud, abbreviated SMC, lies approximately 200,000 light-years away, with total mass around 7 billion solar masses and roughly 3 billion stars. The SMC is more irregular than the LMC, lacking clear spiral structure. It forms a barred irregular galaxy with an elongated shape resulting from tidal interactions with the LMC and Milky Way. The SMC's metallicity heavy element abundance is roughly 1/5 solar value, significantly lower than the LMC's half solar metallicity. This metal deficiency reflects the SMC's smaller mass and lower star formation rate over cosmic history, producing fewer supernovae and thus enriching the interstellar medium less. The SMC's low metallicity makes it valuable for studying stellar evolution under conditions resembling the early universe when heavy elements were scarce. Observations show that the SMC and LMC are not in orbit around each other, but are interacting gravitationally while both orbit the Milky Way. They may have approached each other closely roughly 100 million years ago, triggering enhanced star formation visible in young stellar populations. The Sagittarius Dwarf Elliptical Galaxy, discovered only in 1994, despite its proximity at 70,000 light-years, lies hidden behind the galactic bulge from Earth's perspective. Obscured by stars and dust in the Milky Way's disk, the dwarf galaxy is being tidally disrupted gravitational tides from the Milky Way, stretching it along its orbit, forming the Sagittarius stream that wraps around the Milky Way multiple times. The dwarf contains approximately 1 billion stars, with total mass around 100 million solar masses remaining in the bound core, while several times this mass has been stripped into the stream. Studies of the stream's geometry constrain the Milky Way's gravitational potential and dark matter distribution. The Sagittarius dwarf's discovery demonstrated that the Milky Way actively accretes and destroys satellite galaxies, growing through galactic cannibalism. Several globular clusters, including M54, Terzan 7, and ARP2, are now recognized as having originated in the Sagittarius dwarf, captured by the Milky Way as the dwarf was disrupted. The Canis Major Dwarf Galaxy, announced in 2003 as the nearest known dwarf galaxy at 25,000 light-years distance, remains controversial. The putative galaxy was identified as an overdensity of red giant stars and star clusters near the galactic plane in Canis Major constellation, interpreted as the core of a disrupting dwarf galaxy. However, subsequent analyses question whether this overdensity represents a separate galaxy or merely a dense region in the Milky Way's disk, possibly associated with the outer disk or warp. The debate continues, with some studies supporting the dwarf galaxy interpretation, while others attribute the overdensity to disk structure. If confirmed, Canis Major would be heavily disrupted, contributing stars and clusters to the Milky Way's outer disk. The controversy highlights challenges in identifying disrupted satellites against the Milky Way's complex stellar populations and in distinguishing genuine dwarf galaxies from disk substructure. Approximately 60 satellite galaxies orbit the Milky Way, with discoveries continuing as surveys detect fainter and more distant objects. The count includes classical dwarf spheroidal and irregular galaxies known for decades, plus ultra-faint dwarf galaxies discovered in large area surveys like the Sloan Digital Sky Survey. Ultra-faint dwarfs contain only thousands to tens of thousands of stars, comparable to globular clusters, but differ in having much lower surface brightnesses and higher mass-to-light ratios, indicating dark matter domination. The faintest satellites have luminosities only 1,000 times the Sun's, corresponding to absolute magnitudes around -2, requiring sensitive surveys and careful statistical analysis to detect against foreground stars. The satellite population traces the Milky Way's dark matter halo structure and tests galaxy formation predictions. Cold dark matter simulations predict hundreds to thousands of dark matter subhalos should exist around galaxies like the Milky Way, yet only 60 luminous satellites are observed. This missing satellites problem suggests either that many subhalos failed to form stars, that small satellites were destroyed by tidal forces, or that dark matter properties differ from cold dark matter assumptions. The Magellanic Stream is a massive arc of neutral hydrogen gas, extending over 600,000 light-years across the sky, trailing behind the large and small Magellanic Clouds as they orbit the Milky Way. Discovered in 1974 through 21 centimeter radio observations, the stream contains roughly 200 million solar masses of gas stripped from the Magellanic Clouds through tidal interactions and ram pressure. The resistance the clouds experience moving through the Milky Way's gaseous halo. The stream's morphology and kinematics constrain the Magellanic Cloud's orbital history and the Milky Way's dark matter distribution. Modelling suggests the stream formed over the past 2 billion years during multiple close passages of the clouds near the Milky Way. Gas clouds within the stream are falling back toward the galactic disk, where they will eventually trigger star formation as they merge with disk gas, contributing to the Milky Way's ongoing growth and evolution. The leading arm, a related structure extending ahead of the Magellanic Cloud's orbital motion, contains gas being pulled gravitationally toward the Milky Way. This gas, totaling roughly 50 million solar masses, extends 90 degrees across the sky from the Magellanic Cloud's current positions. The leading arm's existence indicates complex gas dynamics beyond simple tidal stripping interactions between the Magellanic Clouds. Ram pressure from the Milky Way's halo and magnetic fields shape the gas distribution. The leading arm will collide with the Milky Way's disk in approximately 100 million years, raining down fresh gas onto the disk and potentially triggering star formation. Chemical analysis of the leading arm shows metal abundances consistent with the Magellanic Clouds, confirming its origin. The stream and leading arm demonstrate that the Milky Way continues accreting material from satellites, a process contributing to galactic growth throughout cosmic history. The future merger of the Large Magellanic Cloud with the Milky Way is predicted within 2.5 billion years based on the LMC's current trajectory and velocity. As the LMC spirals inward through dynamical friction gravitational drag from the Milky Way's dark matter halo, it will eventually collide with the Milky Way's disk, triggering intense star formation and potentially disturbing the disk's structure. The merger will increase the Milky Way's mass by roughly 1%, modest compared to the eventual Andromeda-Milky Way merger, but still significant for galactic evolution. During the merger, the LMC will be tidally disrupted, its stars dispersing into the Milky Way's halo and disk, while its gas contributes to a starburst. The LMC contains approximately 1 billion solar masses of gas, which will fuel new star formation when shocked and compressed during the collision. Simulations predict the merger might also perturb the Milky Way's central supermassive black hole, possibly triggering an active galactic nucleus phase as gas funnels inward. The Andromeda Galaxy and M33. The Andromeda Galaxy, catalogued as Messier 31 or M31, lies approximately 2.54 million light-years from Earth, making it the nearest large spiral galaxy and the most distant object easily visible to the naked eye. Andromeda contains an estimated 1 trillion stars, roughly 2.5 times more than the Milky Way's 200 to 400 billion, distributed across a disk, approximately 220,000 light-years in diameter, significantly larger than the Milky Way's 100,000 to 180,000 light-year extent. Total mass reaches approximately 1.5 trillion solar masses, including dark matter, comparable to or slightly exceeding the Milky Way's mass depending on measurements. Andromeda appears as an elongated fuzzy patch spanning 3 degrees 6 moon diameters on the sky, though only the bright central region is visible without optical aid. The galaxy's bluish hue indicates active star formation in spiral arms, with an estimated star formation rate around 1 solar mass per year. Persian astronomer Abdulrahman al-Sufi described Andromeda as a small cloud in 964 AD, making it the first galaxy observed beyond the Milky Way, though its extragalactic nature remained unknown until Edwin Hubble's 1923 discovery of Cepheid variable stars proving Andromeda's enormous distance. M31's mass estimate of 1.5 trillion solar masses comes from multiple measurement techniques, including stellar kinematics, satellite galaxy orbits, and globular cluster velocities. Early estimates suggested Andromeda significantly exceeded the Milky Way's mass, but refined measurements indicate comparable masses within uncertainties. The Milky Way might contain slightly more dark matter in its extended halo, while Andromeda has more stellar mass. Both galaxies classify as large spirals, though not the largest galaxies like NGC 6872 and UGC 2885 exceed 800,000 light-years in diameter. Andromeda hosts approximately 450 globular clusters, roughly 3 times the Milky Way's 157, suggesting more vigorous early star formation or different formation history. The globular clusters divide into metal-poor halo clusters and metal-rich disk clusters, similar to the Milky Way, indicating analogous formation through hierarchical assembly. Andromeda's central supermassive black hole contains approximately 100 million solar masses based on stellar kinematics near the nucleus, roughly 25 times more massive than Sagittarius A star's 4 million solar masses. The diameter of 220,000 light-years makes Andromeda the local group's largest galaxy, though comparing sizes requires careful definition. Does size mean the extent of detectable starlight, or the radius encompassing a fixed fraction of total mass, or the virial radius where gravity balances cosmic expansion? Optical observations trace Andromeda's disk to roughly 110,000 light-year radius, where surface brightness drops below detection thresholds, but extended stellar halos, detected through resolved star counts, reach 220,000 light-years. These extended halos contain ancient metal-poor stars from tidally disrupted satellites, analogous to the Milky Way's stellar halo. Deep imaging reveals tidal streams, loops, and shells, fossil evidence of past mergers extending even farther. The virial radius, encompassing the dark matter halo, reaches approximately 750,000 light-years, beyond which matter is no longer gravitationally bound to Andromeda. Within this radius, Total mass including dark matter is approximately 1.5 trillion solar masses. Andromeda approaches the Milky Way at approximately 110 kilometers per second, determined spectroscopically through the Doppler shift of Andromeda's spectral lines. This blue shift wavelength compression indicating approach contrasts with the redshifts of most galaxies receding due to cosmic expansion. Andromeda's approach results from gravitational attraction overcoming the local expansion of space. The two galaxies, separated by 2.54 million light-years, exert mutual gravitational pulls strong enough to bind them as a system. Proper motion measurements using the Hubble Space Telescope and Gaia spacecraft reveal Andromeda's tangential motion across the sky, showing the approach is nearly head-on with minimal tangential velocity. This indicates a collision is inevitable. The galaxies will not miss each other, but will undergo a direct merger. The approaching velocity of 110 km per second seems modest compared to galactic orbital speeds, but over 4.5 billion years, this velocity carries Andromeda across the 2.54 million light-year gap. M33, the Triangulum galaxy, lies approximately 2.73 million light-years away, slightly farther than Andromeda, making it the third largest member of the local group after Andromeda and the Milky Way. M33 contains roughly 40 billion stars, with total mass around 50 billion solar masses, making it significantly smaller and less massive than its two larger neighbours. The galaxy spans approximately 60,000 light-years in diameter, displaying a face-on spiral structure with prominent star-forming regions visible in optical and ultraviolet images. M33 is visible to the naked eye under dark skies, though barely, at apparent magnitude 5.7. The galaxy shows active star formation with a rate around 0.5 solar masses per year, concentrated in spiral arms, and the giant HII region, NGC 604, one of the largest known star-forming regions in the local group, spanning 1,500 light-years and containing over 200 hot young stars. M33's proximity makes it valuable for studying spiral structure, star formation, and stellar populations in detail, impossible for more distant galaxies. Andromeda's satellite galaxies number at least 14 confirmed dwarf galaxies, including M32 and M110-2, bright elliptical dwarfs visible in small telescopes, plus numerous faint dwarf spheroidals discovered through deep surveys. M32, located only 22,000 light-years from Andromeda's center, is a compact elliptical containing roughly 3 billion stars. Tidal interactions with Andromeda have stripped M32's outer regions, compacting the remaining core. M110, lying 200,000 light-years from Andromeda, is a more extended dwarf elliptical, with approximately 10 billion stars. Observations reveal tidal streams connecting M110 to Andromeda, indicating ongoing tidal stripping similar to the Sagittarius dwarf's disruption around the Milky Way. Ultra-faint dwarf satellites around Andromeda, analogous to Milky Way ultrafaints, continue to be discovered. The satellite population provides clues about dark matter substructure and tests galaxy formation predictions from cosmological simulations. The collision timeline predicts first close passage between the Milky Way and Andromeda in approximately 4.5 billion years, based on current positions, velocities, and mutual gravitational attraction. Simulations incorporating uncertainties in masses and velocities suggest first passage occurs 3.9 to 5.1 billion years hence, with 4.5 billion years the median estimate. During first passage, the galaxies won't immediately merge, but will swing past each other in a complex gravitational dance, tidal forces will distort both galaxies' structures, triggering starbursts as gas clouds collide and compress. Stars themselves rarely collide due to vast interstellar spacing. Even in crowded galactic cores, stellar separations enormously exceed stellar sizes. But gas clouds collide, shock, and form stars at enhanced rates. After first passage, the galaxies will separate, reach maximum separation roughly 1 billion years later, then fall back together for a second passage. Multiple passages occur over 2 to 3 billion years, with each passage dissipating orbital energy through dynamical friction, gravitational drag from dark matter interactions until the galaxies merge completely approximately 7 billion years from now. The merger product, informally dubbed Milky or Milkdromeda, will be a giant elliptical galaxy containing roughly 1.4 trillion stars, the combined stellar populations minus stars ejected during the merger. Elliptical galaxies form through major mergers between spiral galaxies of comparable mass. The merger destroys spiral structure stars from both disks, thoroughly mixed through violent relaxation, a process where rapid, time-varying gravitational potentials redistribute stellar energies and angular momenta, producing a spheroidal distribution. Star formation will spike during the merger as gas clouds collide, creating a starburst potentially forming 100 solar masses per year, 100 times current rates for 100 million years. This starburst will consume most remaining gas, after which star formation will cease and the merged galaxy will evolve passively. Supermassive black holes from both galaxies Sagittarius A star and Andromeda's 100 million solar mass black hole will spiral together, eventually merging into a single black hole around 104 million solar masses after emitting gravitational waves. The merger transforms two gas-rich, star-forming spirals into a gas-poor quiescent elliptical, a transformation common in the universe's evolutionary history. Local group structure. The local group extends approximately 10 million light-years in diameter, encompassing the gravitationally bound collection of galaxies including the Milky Way, Andromeda, Triangulum, and over 80 smaller dwarf galaxies. The group's mass totals roughly 2 trillion solar masses, approximately 1.5 trillion from Andromeda, including dark matter 1.5 trillion from the Milky Way, and modest contributions from M33 and dwarfs. The local group's boundary is defined as the zero-velocity surface, where gravitational attraction from group members balances cosmic expansion. Within this boundary, galaxies are gravitationally bound and will not participate in cosmic expansion. They're decoupled from the Hubble flow. Beyond roughly 5 to 6 million light-years from the local group's center, cosmic expansion dominates and galaxies recede. The local group is relatively isolated, separated from nearby groups like the M81 group and Centaurus A group by voids 10 to 15 million light-years across. This isolation allowed the local group to evolve relatively independently rather than merging with neighboring structures. The group contains approximately 80 identified member galaxies, including 54 confirmed members and roughly 30 candidate members pending confirmation through distance and velocity measurements. The count increases continuously as surveys discover fainter and more distant dwarfs. Member confirmation requires determining whether a galaxy's position and velocity indicate gravitational binding to the group rather than being a foreground or background object along the same line of sight. Most members are dwarf galaxies, irregular dwarfs like the Magellanic Clouds with ongoing star formation, or dwarf spheroidals that are gas-poor and inactive. Only 3 large galaxies exist: Andromeda, Milky Way, and M33. This hierarchy, with two dominant galaxies and numerous small satellites, typifies galaxy groups. The dominance of dwarf galaxies reflects the bottom-heavy mass function. Low-mass galaxies are intrinsically far more numerous than massive galaxies across the universe. The two major galaxies, Milky Way and Andromeda, dominate local group dynamics through their mutual gravitational interaction and their influences on satellite orbits. They comprise roughly 95% of the local group's stellar mass and most of its dark matter. Their approaching velocities and eventual merger will transform the local group into a single massive galaxy surrounded by satellites. M33, the third largest member, is intermediate, large enough to have significant mass, but smaller than the two giants. M33's relationship to Andromeda remains unclear. Some models suggest M33 orbits Andromeda as a satellite, while others propose M33 is an independent galaxy passing through the local group. Velocity measurements indicate M33 moves toward Andromeda at roughly 180 km per second, suggesting gravitational interaction. During the Milky Way-Andromeda merger, M33 will likely be disrupted or captured, becoming a satellite of the merged Milky galaxy. The remainder of local group galaxies are dwarf irregulars, dwarf spheroidals, and dwarf ellipticals, with masses ranging from 10 million to few billion solar masses. Dwarf irregulars, like the Magellanic Clouds, contain gas and exhibit active star formation with blue colours, indicating young stellar populations. Dwarf spheroidals are gas-poor, with predominantly old red stellar populations, indicating star formation ceased billions of years ago. The dichotomy suggests environmental effects. Dwarf irregulars reside in the local group's outskirts, where gas stripping is minimal, while dwarf spheroidals orbit close to massive galaxies, where tidal forces and ram pressure stripped their gas. The ultrafaint dwarfs discovered since 2005, with luminosities only thousands of solar luminosities, represent the faintest galaxies known. These systems have mass-to-light ratios exceeding 1,000 solar units, far above typical values, around 5, indicating extreme dark matter domination. They provide tests of dark matter models and galaxy formation in low-mass halos. The barycenter, the center of mass of the local group, lies between the Milky Way and Andromeda, approximately 1 million light-years from each galaxy. This point represents the gravitational center around which both galaxies orbit. The Milky Way and Andromeda currently approach at 110 km per second, but also orbit their common center of mass with velocities determined by the mass distribution. Because Andromeda is slightly more massive, the barycenter lies slightly closer to Andromeda, and the Milky Way orbits with slightly higher velocity. This orbital motion is measured through proper motion's angular position changes over time. The Hubble Space Telescope measured Andromeda's proper motion, showing minimal tangential velocity, confirming the approach is nearly radial head-on rather than involving significant orbital angular momentum that might cause the galaxies to miss. Velocity dispersion within the local group, the spread of galaxy velocities relative to the group's center of mass, is approximately 60 km per second. This relatively low dispersion reflects the group's modest total mass. More massive groups and clusters have higher dispersions. Galaxy clusters show dispersions 500 to 1,000 km per second. The velocity dispersion relates to mass through the virial theorem. Kinetic energy from random motions equals half the gravitational potential energy in virialized systems in dynamical equilibrium. Measuring velocity dispersion for member galaxies and applying the virial theorem yields total mass. For the local group, this method confirms masses around 2 trillion solar masses, consistent with estimates from satellite kinematics and timing arguments comparing the group's past and present configurations. Isolation from surrounding groups means the local group evolved with minimal external perturbations. The nearest significant structures, M81 group at 12 million light-years, Centaurus A group at 13 million light-years, and the more distant Virgo cluster at 54 million light-years, are far enough that tidal forces and gravitational interactions are negligible. This isolation allowed the Milky Way and Andromeda to grow through accretion of gas and small satellites without major mergers disrupting their disk structures. Comparison with galaxies in denser environments shows that environment profoundly affects galaxy evolution. Cluster galaxies undergo frequent mergers, gas stripping through ram pressure as they move through hot intra-cluster gas, and harassment, rapid close encounters disrupting structure. Local group galaxies avoided these effects, preserving spiral structures and ongoing star formation until the impending Milky Way-Andromeda merger transforms the system. Nearby galaxy groups Maffei and Sculptor. Maffei 1, a giant elliptical galaxy lying approximately 10 million light-years away in the constellation Cassiopeia, remains one of the nearest large galaxies to the local group, yet was discovered only in 1968 by Italian astronomer Paolo Maffei during infrared sky surveys. The galaxy's late discovery, despite its proximity and substantial size, containing several hundred billion stars with total mass comparable to the Milky Way, results from its unfortunate position directly behind the zone of avoidance, the region of sky near the galactic plane where the Milky Way's dust lanes absorb and scatter light from background objects. Optical observations in visible wavelengths reveal only a faint smudge due to extinction exceeding 5 magnitudes, reducing apparent brightness by a factor of 100. Infrared observations at wavelengths 2 to 10 microns penetrate this dust effectively, because infrared photons scatter less than optical photons, revealing Maffei 1's enormous stellar population and confirming its nature as a massive elliptical galaxy. The discovery demonstrated that significant structures might remain hidden behind the zone of avoidance, prompting systematic infrared surveys that subsequently discovered additional obscured galaxies, including Maffei 2 and the IC 342 group. Maffei 1 anchors the IC 342. Maffei group, a galaxy group containing at least 10 member galaxies, including IC 342, Maffei 2, and several dwarf galaxies, located approximately 10 to 13 million light-years away, depending on the specific member IC 342, also called Caldwell 5, is a face-on spiral galaxy, heavily obscured by Milky Way dust, that reduces its apparent brightness from what would be a spectacular naked-eye object to barely visible in amateur telescopes. Infrared and radio observations reveal IC 342 as a large spiral comparable in size to M33, containing active star-forming regions and a central starburst nucleus. The proximity of the IC 342 Maffei group makes it scientifically valuable. It's near enough for detailed studies of individual stars and star clusters using Hubble Space Telescope and large ground-based telescopes, yet distant enough to represent typical galaxy group environments. The group's total mass is estimated around 1 trillion solar masses, including dark matter, with the mass concentrated in Maffei 1, IC 342, and Maffei 2. Gravitational interactions within the group trigger enhanced star formation in some members, evidenced by the active star-forming regions observed in IC 342 and Maffei 2. The Sculptor group, also called the South Polar group, centers approximately 12 million light-years away in the constellation Sculptor, making it one of the nearest galaxy groups outside the local group. The group contains roughly 15 to 20 identified members, dominated by NGC 253, the Silver Dollar Galaxy, or Silver Coin Galaxy, a bright barred spiral visible to small telescopes in the southern hemisphere. NGC 253 spans approximately 90,000 light-years in diameter, comparable to the Milky Way's size, and contains an estimated 100 billion stars. The galaxy is undergoing an intense starburst, forming stars at approximately 1,000 solar masses per year based on ultraviolet and infrared luminosity measurements. This rate exceeds the Milky Way's current star formation rate of 1 to 2 solar masses per year by factors of 500 to 1,000, qualifying NGC 253 as a starburst galaxy. The starburst concentrates in the central few thousand light-years, where gas densities reach 100 to 1,000 times typical disk values, compressed by the galaxy's strong barred structure channeling gas inward along the bar's gravitational potential. NGC 253's starburst results from gas compression triggered by gravitational interactions within the Sculptor group and internal bar-driven dynamics. Gravitational interactions between group members during close passages compress gas clouds, triggering enhanced star formation that propagates through the galaxy as density waves and spiral arm perturbations. The bar structure, an elongated concentration of stars and gas extending from the galactic center, exerts non-axisymmetric gravitational forces that drive gas inward through orbital resonances, accumulating gas in the central regions where it collapses to form stars at prodigious rates. Observations reveal that the starburst produces thousands of young, massive star clusters visible in Hubble images, along with powerful stellar winds and supernova-driven superwinds, hot ionized gas flowing outward at velocities 500 to 1,000 kilometers per second, detected through X-ray emission and optical emission lines. These superwinds carry gas, dust, and metals out of the galactic disk into the halo and intergalactic medium, representing feedback that regulates star formation by removing fuel and heating remaining gas to temperatures too high for gravitational collapse. The M81 group, located approximately 12 million light-years away in the constellation Ursa Major, represents another nearby galaxy group containing roughly 30 to 40 members, dominated by 3 large galaxies, M81, M82, and NGC 3077. M81, also called Bode's Galaxy, is a beautiful grand designed spiral galaxy with prominent spiral arms containing massive star-forming regions and molecular gas concentrations. The galaxy contains approximately 250 billion stars with total mass around 70 billion solar masses, excluding dark matter. M81's spiral structure is likely enhanced by tidal interactions with M82 and NGC 3077 gravitational forces during close passages distort galactic disks, creating or amplifying density waves that manifest as spiral arms. The interaction history is reconstructed from neutral hydrogen 21 cm observations, revealing tidal streamers connecting the 3 galaxies, bridges, and tails of gas stripped during past encounters, extending tens of thousands of light-years. M82, the Cigar Galaxy, serves as the prototype starburst galaxy, the archetype defining the starburst phenomenon, where galaxies form stars at rates 10 to 100 times normal, triggered by interactions, mergers, or bar-driven gas infall. located approximately 300,000 light-years from M81 in projection. M82 experienced a close encounter with M81 roughly 300 million years ago that compressed M82's gas and triggered the current starburst, forming stars at approximately 10 solar masses per year, concentrated in the central kiloparsec. This rate, though modest compared to ultra-luminous infrared galaxies forming hundreds of solar masses per year, dramatically exceeds M82's size expected rate. The starburst powers a spectacular superwind hot ionized gas at 10 million Kelvin, expanding perpendicular to the disk at 1,000 kilometers per second. Visible in X-ray images from Chandra as a bipolar outflow extending 10,000 light-years above and below the galactic plane. Optical images reveal filaments of ionized gas traced by H-alpha emission, showing intricate structure created by supernova explosions and stellar winds expanding into the surrounding medium. NGC 3077, the third major member of the M81 group, is an irregular galaxy showing disturbed morphology resulting from tidal interactions with M81 and M82. With mass approximately 10 billion solar masses, NGC 3077 is smaller than its two larger companions, but plays a significant role in the group's interaction dynamics. Neutral hydrogen observations reveal that NGC 3077 lost substantial gas mass during past close encounters. Tidal forces stripped gas that now populates the intergalactic medium within the M81 group, forming tidal streamers and bridges connecting the three galaxies. This stripped gas contains approximately 1 billion solar masses of neutral hydrogen distributed across the group, representing fuel for future star formation if it cools and condenses. The M81 group provides an excellent laboratory for studying galaxy interactions and their effects on star formation, gas content, and morphology processes fundamental to understanding galaxy evolution throughout cosmic history. Centaurus A, designated NGC 5128, is a peculiar elliptical galaxy located approximately 13 million light-years away in the constellation Centaurus, visible only from southern latitudes. The galaxy appears highly unusual in optical images, a large elliptical galaxy bisected by a prominent dust lane, indicative of a recent merger between an elliptical galaxy and a gas-rich spiral. The merger, occurring 100 million to 1 billion years ago, based on stellar population ages in the dust lane, delivered fresh gas to the elliptical's central regions, fueling both star formation in the dust lane and accretion onto the central supermassive black hole. Centaurus A hosts one of the nearest active galactic nuclei, its black hole, with mass approximately 55 million solar masses measured through gas kinematics and stellar dynamics, accretes matter from a dusty circumnuclear disk at rates around 0.1 to 1 solar masses per year, producing luminosity 10 to the 43rd ergs per second across wavelengths from radio to gamma rays. The central black hole launches a powerful relativistic jet, a highly collimated beam of plasma moving at 99% light speed perpendicular to the accretion disk, extending over 1 million light-years from the nucleus. Radio observations at frequencies 1 to 10 GHz reveal the jet's structure in exquisite detail, a bright, compact core coinciding with the black hole, inner jets extending several thousand light-years, showing knots where shocks accelerate particles, and giant radio lobes regions where the jet terminates and deposits energy into the intergalactic medium, creating diffuse emission spanning hundreds of thousands of light-years. The jet's power, approximately 10 to the 44th ergs per second, derives from rotational energy extracted from the spinning black hole through the Blandford-Znajec mechanism, magnetic fields threading the black hole's ergosphere tap rotational energy, channeling it into the jet. High-energy observations reveal gamma-ray emission from the inner jet, where particles accelerate to TeV energies through relativistic shocks and magnetic reconnection. These galaxy groups, IC 342, Maffei, Sculptor, M81, and Centaurus A, contain 10 to 50 galaxies each spanning 5 to 10 million light-years, representing typical small galaxy groups populating the nearby universe within 15 million light-years of the local group. Galaxy groups are the most common environment for galaxies. Roughly 50% of galaxies reside in groups, 25% in rich clusters, and 25% in the field, isolated or in loose associations. Groups typically contain 1 to 3 large galaxies, spirals or ellipticals, with masses 10 to the 11th to 10 to the 12th solar masses, accompanied by 10 to 50 smaller dwarf galaxies, with masses 10 to the 7th to 10 to the 10th solar masses. Total group masses, including dark matter, range from 10 to the 13th to 10 to the 14th solar masses. These nearby groups provide crucial laboratories for studying galaxy evolution processes, including interactions, mergers, ram pressure stripping, tidal forces, and feedback mechanisms, processes that shape galaxies throughout cosmic history and determine their final properties, including morphology, star formation rate, gas content, and stellar populations. The Virgo cluster. The Virgo cluster, located 53.8 million light-years away, centered in the constellation Virgo, represents the nearest large galaxy cluster and dominates the dynamics of the local supercluster through its enormous gravitational influence. The cluster spans approximately 15 million light-years in diameter and contains between 1,300 and 2,000 galaxies, depending on membership criteria and survey completeness, making it the richest cluster within 100 million light-years. With total mass 1.2 times 10 to the 15th solar masses, 1.2 quadrillion solar masses, or roughly 100,000 times the Milky Way's mass, Virgo's gravity attracts surrounding galaxy groups over distances exceeding 50 million light-years. The local group, despite being 54 million light-years from Virgo's center, experiences gravitational attraction manifested as peculiar velocity deviation from pure Hubble expansion of approximately 200 to 300 kilometers per second toward Virgo. This infall velocity adds to the local group's motion toward more distant attractors, including the Great Attractor and Shapley supercluster, creating complex velocity flows, organizing matter on scales of hundreds of millions of light-years. M87, designated Messier 87 or Virgo A, serves as the Virgo cluster's central dominant galaxy, a massive elliptical sitting at the cluster's gravitational center, accreting galaxies and gas through its enormous gravity. M87 contains approximately 1 trillion stars with total stellar mass around 200 billion solar masses. Though including dark matter, raises total mass to roughly 2 trillion solar masses within 100,000 light-years radius. The galaxy's size reaches approximately 120,000 light-years in diameter for the main body, but a faint stellar halo extends to 600,000 light-years, containing stars stripped from satellite galaxies during tidal disruption. M87 hosts an extraordinary population of roughly 12,000 globular clusters, nearly 100 times more than the Milky Way's 157, reflecting the galaxy's formation through mergers of many smaller galaxies. each contributing its globular cluster system to the growing elliptical. These globular clusters, observable as point sources in Hubble Space Telescope images, provide traces of M87's gravitational potential and assembly history. The Event Horizon Telescope collaboration imaged M87's supermassive black hole in April 2019, producing the first direct image of a black hole's shadow, the dark region where photons are gravitationally captured, surrounded by a bright ring of emission from hot accreting gas. The black hole's mass, measured at 6.5 billion solar masses through stellar kinematics, gas dynamics, and now directly through the shadow's size, makes it one of the most massive black holes known. The black hole accretes matter from surrounding hot gas at rates around 0.1 to 1 solar masses per year, producing luminosity 10 to the 43rd ergs per second, modest for such a massive black hole, indicating low efficiency accretion. The accretion powers a relativistic jet extending over 5,000 light-years from the nucleus at speeds approaching light speed, visible in radio images and traced by knots of emission where shocks accelerate particles to relativistic energies. The jet, launching perpendicular to the accretion disk, derives its power from the black hole's rotational energy extracted through magnetic fields in the Blandford-Snejek process. The cluster's galaxy population shows dramatic morphology-density relation. The fraction of ellipticals and lenticulars versus spirals varies with position in the cluster, reflecting environmental processing that transforms galaxies. In the dense cluster core within 1 million light-years of M87, approximately 80 to 90% of galaxies are ellipticals and lenticulars, early-type galaxies that exhausted their gas and ceased star formation billions of years ago, appearing red due to old stellar populations. Only 10 to 20% are spirals. In contrast, the cluster outskirts beyond 5 million light-years show roughly 50% spirals and 50% early types. The core's elliptical dominance results from processes operating in dense environments, galaxy harassment through rapid close encounters, tidally heating and disrupting disks, ram pressure stripping, removing gas as galaxies move through hot intracluster medium, strangulation cutting off gas supply from the intergalactic medium, and mergers between galaxies, building ellipticals from spiral progenitors. Ram pressure stripping, identified as a primary mechanism transforming cluster galaxies, occurs when galaxies moving through the hot intracluster gas at velocities 500 to 1,500 kilometers per second experience wind pressure that sweeps away their cold interstellar gas. The ram pressure, dynamic pressure from relative motion through a medium, is proportional to gas density times velocity squared. In Virgo's core, where intracluster gas density reaches 1,000 particles per cubic centimeter and galaxy velocities approach 1,000 kilometers per second, ram pressure exceeds the gravitational binding of gas in galactic disks, stripping it away. Observations reveal galaxies in the cluster with one-sided tails of neutral hydrogen and ionized gas trailing behind their motion through the cluster, direct evidence of ongoing stripping. Stripped of gas, these galaxies cannot form new stars existing. Massive stars evolve and die within 10 to 100 million years, leaving only long-lived low-mass stars and turning galaxies red and dead within several hundred million years after gas removal. X-ray observations from Chandra and XMM Newton satellites reveal 10 to the 13th solar masses of hot gas at temperatures 10 to 40 million Kelvin, filling the space between galaxies, emitting X-rays through thermal Bremsstrahlung free radiation where electrons scatter off ions and emit photons. This intracluster medium outweighs the cluster's stellar mass by factors of 5 to 10, though dark matter still dominates at 80% of total mass. The hot gas originated partially from primordial gas captured during cluster formation and partially from gas expelled from galaxies through supernova-driven winds and AGN feedback. The temperature, determined from X-ray spectroscopy, measuring emission line ratios and continuum shape, indicates the gas is in hydrostatic equilibrium pressure, balancing gravity within the cluster's gravitational potential. Measuring the gas temperature and density profile allows calculating the cluster's total mass, including dark matter, through the hydrostatic equilibrium equation, yielding the 1.2 times 10 to the 15th solar mass estimate. The intracluster medium shows complex structure including temperature variations, density fluctuations, and chemical enrichment patterns, revealing the cluster's dynamical history. The core region around M87 displays a cool core gas temperature, dropping from 40 million Kelvin in the outer regions to 10 million Kelvin within 100,000 light-years of M87's center, indicating that gas has cooled through radiative losses over billions of years. However, the cooling rate implied by X-ray luminosity suggests gas should cool much faster than observed, precipitating and forming stars at rates exceeding 100 solar masses per year. The absence of such extreme star formation, the cooling flow problem, indicates energy injection, preventing runaway cooling. The leading solution invokes AGN feedback from M87's black hole. Periodic outbursts inflate bubbles of relativistic plasma visible as cavities in X-ray images, injecting mechanical energy that heats surrounding gas and prevents catastrophic cooling. This feedback mechanism regulates cooling flows in cluster cores throughout the universe. Virgo represents the prototypical rich cluster environment where galaxy evolution proceeds rapidly through processes absent or weak in low-density environments like the field or galaxy groups. The combination of high galaxy density enabling frequent close encounters, high velocity dispersion preventing galaxy mergers from resulting in relaxation to equilibrium, hot dense intracluster medium stripping gas, and environmental strangulation cutting off external gas supply transforms in falling spiral galaxies into gas-poor early types over timescales of several 100 million to 1 billion years. Studies comparing Virgo galaxies to field galaxies of similar mass reveal systematic differences. Virgo spirals have lower gas fractions, redder colors indicating older stellar populations and reduced star formation, and often show asymmetric or disturbed gas distributions indicating ongoing environmental processing. These observational signatures of environmental effects in Virgo inform models of galaxy evolution across cosmic time. Most galaxies pass through cluster environments at some point during their histories, undergoing transformations similar to those occurring in Virgo today, the local supercluster Laniakea. The traditional Virgo supercluster definition, established through galaxy mapping surveys in the 1,950 seconds and 1,960 seconds, encompassed roughly 110 million light-years diameter centered on the Virgo cluster and including the local group along with surrounding galaxy groups and smaller clusters. This structure, containing approximately 100,000 galaxies with total mass around 10 to the 15th solar masses, was defined primarily by galaxy density regions, where galaxy number density exceeded the cosmic average by factors of several. The Virgo supercluster appeared as a flattened distribution, a pancake-like structure with the Virgo cluster at its center, and various groups, including the local group, Ursa Major groups, and others distributed throughout. Early estimates suggested the supercluster measured 200 million light-years across its longest dimension. though later refinements reduced this to 110 million light-years for the main concentration. The local group resides on the Virgo supercluster's outskirts, approximately 65 million light-years from the center, in a relatively sparse region between the Virgo cluster and more distant structures. However, 2014 analysis by Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomered revealed that gravitationally, our region belongs to a much larger structure defined not by density alone but by velocity flows, the pattern of galaxy motions caused by gravitational attraction. Using peculiar velocity measurements for thousands of galaxies, velocities after removing the Hubble expansion component, the team mapped how galaxies move relative to the expanding cosmic background. They identified velocity flow basins, analogous to watersheds on Earth, where water flows downhill toward common drainage points, representing regions where galaxies flow toward common gravitational attractors. This analysis revealed that the local group, Virgo cluster, and surrounding structures all belong to a single enormous supercluster, extending 520 million light-years across, with total mass 10 to the 17th solar masses, 100 times more massive than the traditional Virgo supercluster definition suggested. Laniakea, chosen from Hawaiian meaning immeasurable heaven or immense heaven, appropriately names this vast structure spanning nearly 500 million light-years. The supercluster's boundaries are defined by velocity flow separatrices surfaces, where flow directions diverge, marking transitions between different basins of attraction. Within Laniakea, all galaxies share a common destiny flowing toward the structure's center of mass located near the Great Attractor region, approximately 250 million light-years from the local group. The flow velocities reach 600 to 700 kilometers per second for galaxies deep within the structure, though velocities decrease toward the boundaries where competing attractions from neighboring superclusters like Perseus, Pisces and Shapley become comparable to Laniakea's pull. The structure's discovery transformed understanding of local cosmic structure, demonstrating that gravitational dynamics organize matter on scales approaching 500 million light-years, far larger than previously recognized, and approaching scales where dark energy's repulsive effect begins dominating over gravitational attraction. The structure extends from the Perseus-Pisces supercluster on one side through the Virgo cluster to the Great Attractor region near Norma cluster and Centaurus cluster, encompassing multiple previously identified superclusters, including the traditional Virgo supercluster, Hydra Centaurus supercluster, Pavo Indus supercluster, and parts of the Centaurus supercluster. These smaller structures, defined by density enhancements, represent substructures within the larger velocity-defined basin. The Virgo cluster, despite its proximity, contains only a small fraction of Laniakea's total mass, roughly 1%. Most mass concentrates in more distant regions toward the Great Attractor and Shapley concentration, explaining why our velocity flow points well beyond Virgo toward these more massive attractors. The Shapley concentration at 650 million light-years, though outside Laniakea's boundaries, exerts gravitational influence that affects velocity flows within Laniakea, particularly in regions near the boundary between the two basins of attraction. The local group resides on Laniakea's outskirts, in a relatively underdense region, flowing toward the center at velocities exceeding 600 kilometers per second when accounting for all velocity components. This motion results from the combined gravitational attractions of Virgo cluster, pulling at 200 to 300 kilometers per second, the Great Attractor region contributing another 200 to 300 kilometers per second, and more distant masses in the Shapley region adding their influence. The peculiar velocity are deviation from pure Hubble expansion was recognized decades ago through observations showing that our velocity relative to the cosmic microwave background rest frame is 630 kilometers per second toward A direction in Hydra Centaurus, but identifying the specific mass concentrations causing this motion required mapping galaxy distributions and velocities across hundreds of millions of light-years. Laniakea's definition finally explained these motions as our position within a vast supercluster flowing toward its gravitational center. The discovery transformed understanding of cosmic structure by showing that velocity-based definitions reveal coherent structures invisible to density-based methods. Traditional supercluster definitions identified local density enhancements but missed the broader gravitational connections. Velocity flow methods trace gravitational influence directly, revealing how matter actually moves and which structures are dynamically connected versus merely appearing close in projection. This approach has been applied to map the cosmic web on larger scales, identifying dozens of superclusters like Laniakea throughout the nearby universe within 1 billion light-years. Each supercluster represents a basin of attraction where hundreds of thousands of galaxies flow toward common centers, creating the universe's largest gravitationally bound or semi-bound structures. Beyond roughly 500 million to 1 billion light-years, dark energy's acceleration dominates over gravitational attraction, preventing larger structures from forming and eventually halting infall within existing superclusters. This discovery illustrated how gravitational interactions organize matter on scales approaching 500 million light-years, revealing the cosmic web's three-dimensional structure and dynamics in unprecedented detail. Prior to velocity-based mapping, astronomers knew matter distributed in filaments, walls, and voids, but lacked clear understanding of how these structures dynamically connected. The velocity flow analysis shows that filaments represent streams of galaxies flowing along gravitational gradients towards superclusters. Walls form where flows converge from multiple directions, creating sheet-like structures, and voids represent regions from which matter flows away towards surrounding overdensities. The cosmic web is not static but dynamic, a living structure where galaxies continuously fall along gravitational gradients toward ever larger mass concentrations. Laniakea represents one such concentration, growing over billions of years as galaxies and groups fall inward, though dark energy will eventually freeze this infall and isolate the structure from surrounding regions. The name Laniakea, suggested by Nawaa Napoleon, Associate Professor of Hawaiian Language at Kapiolani Community College, acknowledges the Discovery team's connection to Hawaii. Much of the peculiar velocity data came from observations at telescopes in Hawaii, and team member Brent Tully works at the University of Hawaii. The Hawaiian name appropriately captures the structure's immensity, immeasurable or immense heaven, reflecting both its vast scale and the sense of wonder it inspires. The discovery paper, published in Nature in September 2014, provided the first clear picture of our home supercluster's extent and dynamics, answering questions about local, large-scale structure that had puzzled astronomers for decades. Subsequent work has refined Laniakea's boundaries, identified neighboring superclusters, including Perseus Pisces, Coma, Shapley, and others, and mapped velocity flows throughout the nearby universe, revealing the cosmic web's detailed structure, the Great Attractor, and Shapley concentration. The Great Attractor, located approximately 220 million light-years away in the direction of the Norma cluster behind the galactic plane in the zone of avoidance, represents a massive overdensity causing peculiar velocities, deviations from pure Hubble expansion of 600 kilometers per second for galaxies within 100 million light-years. The anomaly was discovered in the 1970 seconds, when astronomers measuring galaxy redshifts and distances realized that the local group and surrounding galaxy groups moved at several hundred kilometers per second toward a specific direction in the southern sky near the constellations Triangulum, Australe, Norma, and Centaurus, indicating enormous mass concentrations beyond the Virgo cluster, pulling us gravitationally. Initial estimates suggested a single massive object, but subsequent observations revealed a complex region containing multiple galaxy clusters, including the Norma cluster, Centaurus cluster, and additional structures hidden behind Milky Way dust. The total mass within 50 megaparsecs, 160 million light-years radius, reaches approximately 10 to the 16th solar masses, comparable to 100,000 Milky Way galaxies. The great attractor's position behind the galactic plane creates observational challenges. Dust extinction at optical wavelengths exceeds 10 magnitudes in the densest regions, reducing apparent brightness by factors of 10,000 and completely obscuring background galaxies from visual observation. Infrared surveys at 2 to 10 micron wavelengths penetrate much of this dust, revealing numerous galaxies in the Great Attractor region. The 2-micron all-sky survey, mapping the sky at near-infrared wavelengths, identified thousands of previously unknown galaxies behind the zone of avoidance, including major clusters. The Norma cluster emerged as one of the richest clusters in the Great Attractor region, containing over 1,000 galaxies within 10 million light-years and exhibiting high X-ray luminosity from hot intracluster gas, indicating total mass approaching 10 to the 15th solar masses. However, even accounting for all observed clusters, the total mass falls short of explaining the 600 km per second peculiar velocities, suggesting either that significant mass remains undetected behind residual dust, or that more distant structures contribute substantially to the gravitational pull. Beyond the Great Attractor lies the Shapley supercluster at 650 million light-years, the largest concentration of galaxies in the nearby universe, and possibly the most massive structure within 1 billion light-years. Discovered by Harlow Shapley in the 1930 seconds during photographic surveys of galaxy distributions, the Shapley concentration contains 25 or more rich galaxy clusters, including Abell 3558, Abell 3562, and Abell 3571 each, comparable in mass to the Virgo cluster, concentrated within a region roughly 100 million light-years across. The total mass exceeds 10 to the 16th solar masses, possibly reaching 10 to the 17th solar masses when accounting for extended dark matter halos. X-ray observations reveal enormous quantities of hot gas at 10 to 100 million Kelvin, filling the space between clusters, indicating the supercluster is a dynamically evolving structure where clusters are merging and accreting gas. The Shapley concentration's gravity creates even stronger peculiar velocities than the Great Attractor galaxies. Within 300 million light-years, show coherent motions of several hundred kilometers per second toward Essis. Shapley. The Shapley concentration creates gravitational pull, attracting matter from hundreds of millions of light-years away, including the local group, Virgo cluster, and the Great Attractor region itself. Measurements indicate our peculiar velocity has a significant component toward Shapley beyond the Great Attractor, suggesting that Shapley contributes substantially to our motion through space. Some studies propose that Shapley represents the dominant attractor within 1 billion light-years, with the Great Attractor serving as an intermediate concentration between the local group and Shapley, rather than the ultimate source of our peculiar velocity. This hierarchical structure, local concentrations pulling toward larger concentrations, illustrates gravitational structure formation. Matter flows along gravitational gradients from voids toward filaments, from filaments toward clusters, from clusters toward superclusters, creating the cosmic web's characteristic pattern. Shapley represents one of the largest nodes in this web within the nearby universe. Some studies suggest a still larger structure, the Shapley attractor or ultimate attractor, at 700 to 1,000 million light-years exerts influence extending across significant fractions of the observable universe. This hypothetical structure, if it exists, would represent the ultimate mass concentration driving bulk flows within 1 billion light-years. Evidence comes from observations suggesting that peculiar velocities remain coherent galaxies moving in consistent directions rather than random out to 700 to 1,000 million light-years, implying gravitational influences from structures at these distances. However, measuring peculiar velocities at such distances is challenging uncertainties. In distance measurements translate to large velocity uncertainties, and the peculiar velocity signal becomes comparable to measurement errors. Additionally, dark energy's repulsive effect grows stronger at these scales, counteracting gravitational attraction and making it unclear whether structures at 700 to 1,000 million light-years can maintain coherent gravitational influence over such vast volumes. This hierarchical structure, attractors pulling toward larger attractors, illustrates how gravity organizes cosmic structure on ever larger scales, up to the point where dark energy domination prevents further structure growth. On scales below 10 million light-years, individual galaxy groups dominate dynamics. Galaxies orbit within groups. On scales 10 to 100 million light-years, galaxy clusters dominate, groups fall toward clusters. On scales 100 to 500 million light-years, superclusters dominate, clusters fall toward supercluster cores. Beyond 500 million to 1 billion light-years, dark energy's acceleration makes gravitational attraction increasingly ineffective structures cease growing and eventually become isolated as expansion accelerates. The Great Attractor and Shapley concentration represent the largest mass concentrations within our cosmic neighborhood, defining the gravitational landscape, determining how matter moves within several 100 million light-years of the local group. Understanding these structures provides crucial tests of cosmological models. The amplitude of peculiar velocities, how fast galaxies move relative to Hubble expansion, depends on the matter density of the universe and the spectrum of density fluctuations. Measuring velocities across large volumes and comparing to predictions from lambda CDM cosmology tests whether the model correctly describes structure growth from initial fluctuations seen in the CMB to present day structures. Early measurements suggested peculiar velocities were larger than lambda CDM predicted, the so-called bulk flow problem, but improved measurements and simulations largely resolved this discrepancy, confirming lambda CDM predictions within uncertainties. The Great Attractor and Shapley regions represent rare high-mass fluctuations, several sigma peaks in the density field, that form infrequently but exert outsized influence on local dynamics when they do form. The Sloan Great Wall and Cosmic Web. The Sloan Great Wall, discovered in 2003 by J. Richard Gott III and colleagues analyzing Sloan Digital Sky Survey spectroscopic redshift data, extends approximately 1.37 billion light-years in length, with estimated mass around 10 to the 18th solar masses at redshift Z equals 0.073 to 0.083, corresponding to roughly 1 billion light-years distance when light left these galaxies. This massive filamentary structure represents one of the largest coherent structures mapped in the universe, approaching and possibly exceeding the cosmological homogeneity scale the scale beyond which the universe should appear statistically uniform according to the cosmological principle. The structure appears as a vast concentration of galaxies stretching across a significant fraction of the sky, visible in three-dimensional redshift surveys, containing hundreds of galaxy groups and clusters connected by filaments of galaxies and dark matter. The discovery challenged theoretical understanding of structure formation standard. Lambda CDM cosmology predicts maximum structure sizes around 300 to 500 million light-years, making 1.37 billion light-year structures rare but not impossible. The Sloan Great Wall's mass estimate of 10 to the 18th solar masses, 1 quintillion solar masses, or 1 million Milky Ways, comes from counting galaxies within the structure, applying typical mass-to-light ratios, and accounting for dark matter. The structure contains thousands of identified galaxies, with total luminosity exceeding 10 to the 14th solar luminosities. Assuming a mass-to-light ratio around 100 solar units, typical for large-scale structures where dark matter dominates, yields total mass around 10 to the 16th solar masses for visible matter and associated dark matter halos. However, the structure spans such enormous volume that including all dark matter within its boundaries raises total mass estimates to 10 to the 18th solar masses. This represents a lower bound. Some fraction of dark matter between clusters might not be gravitationally bound to the structure, but merely lies along the same line of sight, though velocity studies suggest most is dynamically associated. The structure's location at redshift z, approximately 0.073 to 0.083, places it roughly 1 billion light-years away, meaning we observe it as it appeared 1 billion years ago when the universe was roughly 12.8 billion years old, 93% its current age. At this epoch, cosmic structure had reached maturity. The cosmic web's large-scale pattern of filaments, walls, nodes, and voids had fully developed, though structures continue evolving through accretion and mergers. The Sloan Great Wall represents a mature filament, a long, thin concentration of matter connecting multiple massive galaxy clusters. Simulations show such structures form at the intersections of multiple smaller filaments, creating nodes where galaxy clusters assemble from infalling matter. The Great Wall's length of 1.37 billion light-years corresponds to roughly 400 megaparsecs in comoving coordinates, a scale where cosmic structure transitions from highly non-uniform to approaching statistical homogeneity. This massive filamentary structure represents one of the largest coherent structures mapped in the universe, with only a few comparable structures known, including the CFA, 2 Great Wall, at 750 million light-years discovered in 1989, and the potentially larger Hercules Corona Borealis Great Wall, announced in 2013, with estimated length 10 billion light-years. Though the latter's reality and coherence remain debated, the Sloan Great Wall's existence as a coherent structure is supported by consistent redshift galaxies throughout the structure have similar velocities, indicating they're physically connected rather than chance alignments of separate structures at different distances. Galaxy density within the wall exceeds the cosmic average by factors of 5 to 10, with peak densities in embedded clusters reaching 100 times average. Between dense nodes, the filament maintains moderate overdensity, with galaxies strung along like beads on a string, connected by underlying dark matter filaments traced through gravitational lensing and galaxy velocity measurements. The cosmic web, the large-scale structure's three-dimensional pattern, consists of filaments like the Sloan Great Wall, spanning hundreds of millions of light-years, walls or sheets forming void boundaries, nodes where filaments intersect, containing galaxy clusters, and voids under dense regions, 30 to 500 million light-years across, comprising 50 to 70% of the universe's volume. This structure arose from gravitational instability operating over 13.8 billion years. Initially, quantum fluctuations during inflation created small density variations, 1 part in 100,000, imprinted on matter when inflation ended. These fluctuations, visible in the cosmic microwave background, served as seeds for all subsequent structure. Overdense regions, having slightly more matter than average, exerted slightly stronger gravity, attracting surrounding matter and growing denser. Underdense regions lost matter to surrounding overdensities, expanding and becoming voids. This process operated hierarchically. Small structures formed first, then merged to build larger structures. Filaments are typically 5 to 10 megaparsecs, 15 to 30 million light-years wide, and extend 100 to 500 megaparsecs, 300 million to 1.5 billion light-years long, containing galaxy groups and clusters strung along them. The filaments represent the primary structural elements of the cosmic web, containing roughly 40% of the universe's matter, while occupying only 10% of volume. Galaxies within filaments show preferential alignments. Their angular momenta tend to align parallel to the filament axis, indicating that the large-scale tidal field generated by the cosmic web's structure affects galaxy formation and evolution. Filaments channel gas toward galaxy clusters at their intersections, fueling galaxy formation and cluster growth. Numerical simulations show that most galaxies formed within filaments or fell into them along smaller connecting structures, making filaments the cosmic web's arteries through which matter and galaxies flow. Walls or sheets form where filaments intersect, or where void expansion compresses matter into thin layers at void boundaries. Walls contain galaxy groups and occasional clusters distributed across surfaces tens of millions of light-years across, but only several million light-years thick. The Sloan Great Wall might be better described as a sheet containing multiple embedded filaments rather than a single filament, though terminology varies. Walls comprise roughly 10 to 20% of the universe's volume, containing 20 to 30% of matter. Galaxies in walls show moderate density enhancements and complex kinematics as they fall toward embedded clusters and filaments. The most prominent walls form at the boundaries of large voids, where expansion pushed matter outward, creating shells of enhanced density surrounding evacuated regions. Nodes represent the highest density regions where multiple filaments intersect, creating the gravitational potential wells within which galaxy clusters form. The richest clusters, containing thousands of galaxies and total masses exceeding 10 to the 15th solar masses, invariably occur at nodes connecting 3 or more major filaments. The Coma cluster, Virgo cluster, and Perseus cluster exemplify such nodes in the nearby universe. At nodes, matter flows inward along filaments at velocities reaching 1,000 kilometers per second, feeding cluster growth. The dense environment triggers rapid galaxy evolution through mergers, interactions, gas stripping, and harassment, transforming in falling spiral galaxies into ellipticals and lenticulars over several 100 million years. Clusters at nodes represent the universe's most massive, virialized structures, systems in dynamical equilibrium, where kinetic and gravitational potential energy balance. Voids under dense regions comprise 50 to 70% of the universe's volume depending on definition, yet contain only 10 to 20% of galaxies and matter. Voids range from 30 to 500 million light-years diameter, with typical sizes 100 to 200 million light-years. The largest known void, the Boötes void, discovered in 1981, spans 330 million light-years, yet contains only 60 galaxies, compared to 3,000 expected from cosmic average density. Voids are not completely empty but extremely underdense. Matter density reaches only 10 to 20% cosmic average in typical voids. The few galaxies within voids show distinctive properties. They're predominantly late-type spirals and irregulars, with active star formation, blue colors, and high gas fractions. Void galaxies avoided the environmental processing, affecting galaxies in filaments and clusters, evolving in isolation and retaining their gas and star formation capacity. This structure arose from gravitational instability. Initially, small density fluctuations grew over 13.8 billion years through gravitational amplification. Overdense regions attracted matter, growing denser and eventually collapsing to form galaxies, groups, and clusters. Underdense regions lost matter to surrounding overdensities, expanding faster than cosmic average and becoming increasingly underdense. The process is nonlinear. Matter doesn't simply remain where it started, but flows along gravitational gradients, accumulating in filaments and clusters while evacuating voids. Dark matter, comprising 85% of matter, dominates structure formation because it interacts only gravitationally, allowing it to collapse without pressure support. Baryonic matter follows dark matter's gravitational potential wells, accumulating where dark matter concentrated and forming stars and galaxies. The cosmic web represents the largest scale gravitationally organized structure in the universe, reflecting the transition from nearly uniform conditions at recombination to the highly structured present. Observations from galaxy surveys mapping millions of galaxies across billions of light-years reveal the web's statistical properties: the power spectrum measuring structure, amplitude versus scale, the correlation function quantifying galaxy clustering, and the topology characterizing structure geometry. These measurements constrain cosmological parameters, including matter density, dark energy density, and the spectrum of primordial fluctuations. The cosmic web's detailed structure provides crucial tests of lambda CDM cosmology, comparing observed structure to simulations tests. Whether the model correctly describes gravitational structure formation from known initial conditions to the present. Agreement between observations and predictions across scales from 1 megaparsec to 1000 megaparsecs strongly supports lambda CDM, confirming our understanding of structure formation driven by gravity and dark matter, quasars, and high redshift galaxies. 3C 273, located 2.4 billion light-years away at redshift Z equals 0.158, stands as the brightest quasar in the sky and the first quasar identified in 1963 by Martin Schmidt. The discovery revolutionized astronomy. Schmidt measured enormous redshift indicating vast distance, yet 3C 273 appeared bright enough to photograph with modest telescopes, implying extraordinary intrinsic luminosity, exceeding 4 trillion solar luminosities. This luminosity emanates from a region smaller than the solar system, powered by a billion solar mass black hole accreting matter at roughly 10 solar masses per year. Quasars represent the most luminous, persistent objects in the universe, outshining entire galaxies through energy released as matter spirals into supermassive black holes. The quasar phenomenon dominated cosmic history during the peak epoch of galaxy formation 10 to 11 billion years ago, when gas supplies were abundant and black holes grew rapidly through accretion. Today, quasars are rare. Most supermassive black holes depleted their fuel and became quiescent, like Sagittarius A star. Ulaz J 1000, 342, plus 0928. One of the most distant quasars known lies 13.1 billion light-years away at redshift Z equals 7.54. Observed when the universe was only 690 million years old, 5% its current age. The quasar contains a supermassive black hole with mass approximately 800 million solar masses, posing challenges for theoretical models, explaining how black holes grew so massive so quickly. Standard accretion models, starting from stellar mass black hole seeds formed from first-generation stars, struggle to accumulate 800 million solar masses in only 690 million years, even assuming continuous Eddington-limited accretion. Proposed solutions include supermassive seed black holes formed through direct collapse of massive gas clouds without forming stars first, or super Eddington accretion exceeding standard limits. High redshift quasars, like ULAS J 1342 plus 0928, provide crucial tests of black hole formation theories and constrained conditions in the early universe during the epoch of reionization, when the first luminous sources ionized neutral hydrogen pervading intergalactic space. Quasar density peaked at redshift Z approximately 2 to 3, corresponding to 10 to 11 billion years ago, when the universe was 2 to 4 billion years old. During this epoch, massive galaxies underwent their most vigorous growth through gas accretion and mergers, funneling gas towards central black holes and igniting quasar activity. Surveys mapping quasar distributions across cosmic time reveal the quasar luminosity function. The number density of quasars at different luminosities evolved dramatically, with peak activity occurring when the universe was 1/4 to 1/3 its current age. The decline since reflects gas depletion, star formation, and previous quasar activity consumed or expelled gas, starving black holes of fuel. Additionally, AGN, feedback energy and momentum output from accreting black holes, heats and expels gas from galaxies, self-regulating growth. The correlation between quasar activity and cosmic star formation history, both peaking around Z equals 2, suggests intimate connections between black hole growth and galaxy evolution. Galaxy evolution proceeds through characteristic stages, observable by looking at increasingly distant and thus earlier cosmic epochs. At low redshift Z less than 1, massive galaxies divide into blue, star-forming spirals and red quiescent ellipticals. The blue cloud contains gas-rich spirals, forming stars at modest rates around 1 to 10 solar masses per year. The red sequence contains gas-poor ellipticals and lenticulars, with star formation ceased billions of years ago, containing only old red stars. At intermediate redshift Z equals 1 to 2, galaxies are more irregular and disturbed, showing higher merger rates and intense star formation. Many are dusty starburst galaxies, forming stars at hundreds of solar masses per year. At high redshift Z greater than 2, galaxies are smaller, more irregular, and highly star-forming. The massive galaxies present at low redshift are assembling through mergers of these smaller progenitors. Tracking galaxy properties across cosmic time reveals hierarchical assembly. Small galaxies merge to build larger ones, and downsizing massive galaxies formed most of their stars early, while low-mass galaxies continue forming stars to the present. Look-back time. The time elapsed since light left distant objects increases with redshift, allowing observations to trace cosmic history. At Z equals 1, look-back time is approximately 8 billion years. At Z equals 2, look-back time reaches 10.3 billion years. At Z equals 3, we observe the universe at 11.5 billion years ago. The relationship between redshift and look-back time depends on cosmological parameters, including matter density, dark energy density, and expansion history. For current cosmology, with matter density parameter 0.3 and dark energy density parameter 0.7, the relationship is nonlinear. Early universe redshifts correspond to smaller time intervals because the universe expanded more rapidly when denser. At z equals 7.54, like Euler's J1000, 342 plus 0928, look-back time is 13.1 billion years. At z equals 11, look-back time exceeds 13.4 billion years, observing galaxies formed only 400 million years after the Big Bang. Each increase in observable redshift pushes closer to the universe's beginning. GNZ 11, detected by Hubble Space Telescope at redshift z equals 11.09, held the distance record for confirmed galaxies prior to James Webb Space Telescope operations. Located 13.4 billion light-years away, GNZ 11 is observed 400 million years after the Big Bang, when the universe was 3% its current age. The galaxy, despite its youth, formed stars at roughly 20 solar masses per year and had already accumulated approximately 1 billion solar masses of stars. Such rapid early assembly challenges models predicting more gradual galaxy growth. The galaxy's detection at such high redshift was possible due to gravitational lensing magnification. A foreground galaxy cluster gravitationally amplified GNZ11's light by factors of several, bringing it above detection thresholds. Without lensing, galaxies at Z greater than 10 remained undetectable until JWST's superior infrared sensitivity enabled routine detections at these redshifts. JWST discoveries include galaxies at redshifts Z greater than 12 to 13, observed less than 300 million years after the Big Bang, revealing unexpectedly mature galaxies with significant stellar masses and complex structures. Early JWST surveys found galaxy candidates at Z approximately 12 to 16, though spectroscopic confirmation remains challenging at such extreme distances. These galaxies appear more luminous and structured than models predicted for such early epochs, suggesting either that star formation efficiency was higher in the early universe, or that galaxy assembly proceeded faster than standard models indicate. Alternatively, some candidates might be lower redshift dusty galaxies mimicking high redshift signatures. Spectroscopic follow-up distinguishes these scenarios. The reionization epoch, spanning 150 million to 1 billion years after the Big Bang, when the first stars and galaxies ionized neutral hydrogen pervading intergalactic space, is now being directly observed. JWST observations constrain when reionization occurred, which sources contributed massive stars, black holes, or both, and how ionization fronts propagated through the universe. The reionization epoch transformed the universe from neutral to ionized as the first luminous sources, population 3, stars in the first galaxies and early quasars emitted ultraviolet photons, stripping electrons from hydrogen atoms. Before reionization, the universe was filled with neutral hydrogen absorbing UV radiation, rendering it opaque to wavelengths below the Lyman alpha transition at 121, 6 nanometers. Reionization made the universe transparent, allowing UV and optical photons to propagate freely. The timing and duration of reionization remain active research areas. Cosmic microwave background observations from Planck satellite constrain reionization to complete by Z approximately 6, around 1 billion years after the Big Bang. JWST observations push the frontier earlier, detecting galaxies at Z greater than 10, suggesting reionization began earlier than previously thought. Understanding reionization requires identifying the ionizing sources. Massive stars produce UV photons, but many are absorbed by dust. Black holes produce harder radiation penetrating dust, but might be rarer. The relative contributions determine reionization morphology and timeline. The cosmic microwave background surface. The cosmic microwave background, abbreviated CMB, represents the oldest light observable in the universe. Emitted 380,000 years after the Big Bang from a co-moving distance of 46.1 billion light-years, when accounting for cosmic expansion that occurred during the light's 13.8 billion-year journey to Earth. The CMB's current distance, the distance to the surface of last scattering in today's coordinates, is 46.1 billion light-years, despite the universe being only 13.8 billion years old, because space expanded during the light's transit. When CMB photons began their journey, the universe was much smaller and denser. The light travel distance is 13.8 billion light-years, but expansion carried the emission region farther away continuously, resulting in the much larger co-moving distance. The CMB appears as a nearly uniform glow at microwave wavelengths, surrounding us in all directions, the cooled and redshifted remnant of the hot, dense, early universe. The universe's age, when the CMB was emitted, was precisely 380,000 years. Determined from detailed modelling of recombination physics, the process where free electrons combined with protons to form neutral hydrogen atoms. Before recombination, the universe consisted of ionized plasma, where photons constantly scattered off free electrons through Thomson scattering, keeping matter and radiation tightly coupled in thermal equilibrium. As the universe expanded and cooled, temperature dropped below approximately 3000 Kelvin, allowing electrons and protons to combine into neutral atoms. Neutral hydrogen doesn't scatter photons efficiently at microwave wavelengths, so photons decoupled from matter and streamed freely through space. This decoupling occurred relatively abruptly over roughly 100,000 years, centered at 380,000 years after the Big Bang. The surface of last scattering represents the shell surrounding us from which we received these decoupled photons the last time they interacted with matter. Redshift of the CMB is approximately Z equals 1,100, calculated from the ratio of emission temperature to observed temperature. When emitted, the CMB had temperature 3000 Kelvin, hot enough to glow orange-red like a light bulb filament. The universe has expanded by a factor of 1,100 since then, stretching photon wavelengths by the same factor and reducing temperature proportionally. The CMB's current temperature is 2.725 Kelvin, measured precisely by the COB, WMAP, and Planck satellites. This corresponds to peak emission at microwave wavelengths around 2 mm. The redshift temperature relationship is T equals T0 divided by 1 plus Z, where T0 is today's temperature. Solving gives Z equals 1099.7, conventionally rounded to 1100. This enormous redshift indicates the light has travelled through 13.8 billion years of cosmic expansion, being stretched by over 3 orders of magnitude. The temperature, when emitted, was 3000 Kelvin, corresponding to the recombination temperature where neutral hydrogen formation became efficient. At temperatures above 3000 Kelvin, thermal photons carry sufficient energy to ionize hydrogen atoms. Ultraviolet photons, with energies exceeding the 13.6 electron-volt ionization energy, are abundant in the thermal distribution. Below 3000 Kelvin, the fraction of photons energetic enough to ionize atoms drops exponentially, allowing neutral atoms to persist. The recombination process followed a 2-step sequence. First, electrons recombined directly to the ground state, emitting Lyman alpha photons. These photons immediately ionized neighboring atoms, maintaining ionization. Eventually, recombination through excited states, producing lower energy Balmer photons that couldn't ionize ground state atoms, broke the cycle, allowing neutral fraction to rise rapidly. The epoch of recombination converted the universe from 90% ionized to 90% neutral over roughly 100,000 years, centered at 380,000 years post-Big Bang. The temperature today is 2.725 Kelvin, established through precise measurements by satellite missions. COPE satellite in 1989 measured the CMB spectrum, finding perfect blackbody form consistent with thermal radiation from a uniform temperature source. The temperature determination achieved precision, 1 part in 100,000. WMAP and Planck satellites refined this to parts per million. The CMB's blackbody spectrum is the most perfect blackbody known, confirming the hot Big Bang model's prediction of thermal equilibrium in the early universe. Small deviations from perfect blackbody spectral distortions would indicate energy injection or dissipation, but none are detected within current sensitivities, constraining possible deviations from standard cosmology to extremely low levels. The temperature's precise value is fundamental. It fixes the CMB photon density at approximately 411 photons per cubic centimeter, vastly outnumbering atoms at 0.25 per cubic centimeter. Temperature fluctuations across the sky amount to approximately 1 part in 100,000. The CMB is extraordinarily uniform. After removing the dipole anisotropy, the apparent temperature difference between directions due to Earth's motion relative to the CMB, rest frame residual fluctuations, are only 18 microkelvin root mean square on degree. Angular scales. These tiny fluctuations, detected by COBE in 1992 and mapped in exquisite detail by WMAP and Planck, represent primordial density fluctuations, regions slightly denser or less dense than average at recombination. Overdense regions appear hotter because gravitational potential wells cause photons to blue shift as they climb out the Sachs-Wolf effect. Acoustic oscillations, sound waves in the photon baryon plasma before recombination, created a characteristic pattern of hot and cold spots on angular scales corresponding to the sound horizon at recombination. Analyzing fluctuation patterns measures cosmological parameters, including geometry, composition, and expansion history, with percent-level precision. Acoustic peaks in the CMB power spectrum, the plot showing fluctuation amplitude versus angular scale, reveal the universe's geometry, density, and composition. The first acoustic peak at angular scale 1 degree corresponds to the sound horizon, the distance sound waves traveled in the photon baryon plasma from Big Bang to recombination, approximately 150,000 light-years at recombination, subtending 1 degree on the sky for flat geometry. If the universe were positively curved, the sound horizon would subtend larger angle. If negatively curved, smaller angle. Observations confirm flat geometry within 0.5%. Peak ratios constrain baryon density. More baryons enhance odd-numbered peaks relative to even peaks because baryons add inertia to compressions while reducing rarefactions. Observations indicate baryons comprise 5% of total density. Dark matter comprises 27%, inferred from peaks' detailed shapes and small-scale power. Dark energy comprises 68%, inferred from distance measurements and cosmic acceleration. The CMB acoustic peaks provide the most precise cosmological measurements available. The last scattering surface represents the boundary of the observable universe's beginning, the earliest epoch from which electromagnetic radiation reaches us directly. Earlier epochs including the Dark Ages before first stars formed and the first 380,000 years before recombination, cannot be observed electromagnetically because photons were trapped in opaque plasma. However, gravitational waves and neutrinos from these epochs would propagate freely. Future gravitational wave observatories might detect primordial gravitational waves from inflation or cosmic strings, probing pre-recombination epochs. Neutrino observatories could detect the cosmic neutrino background from 1 second after the Big Bang, when neutrinos decoupled. But for electromagnetic observations, the CMB represents the ultimate horizon we cannot see earlier directly. Everything we know about earlier times comes from indirect inference through CMB imprints, light element abundances from Big Bang nucleosynthesis, and theoretical extrapolation from known physics. Observational limits and the particle horizon. The particle horizon, defining the maximum distance from which light could have reached us during the universe's 13.8 billion year age, extends 46.5 billion light-years in co-moving coordinates, the distance to the horizon in today's universe after accounting for expansion. This co-moving radius exceeds the universe's age times the speed of light, because space expanded while photons travelled toward us. A photon emitted from the edge of the observable universe when it was very young travelled a certain proper distance through space, but during its journey, space itself expanded, increasing the distance between its emission point and Earth. The co-moving distance accounts for this expansion, representing where the emission point is located now in today's coordinates. The observable universe's diameter is twice the co-moving radius, 93 billion light-years across, containing everything from which light could have reached us since the Big Bang. This represents the observable universe, our cosmic horizon beyond which information cannot reach us given finite age and finite light speed. The particle horizon grows over time as light from increasingly distant regions reaches us, though dark energy acceleration will eventually halt this growth. The observable universe diameter of 93 billion light-years encompasses everything observable through electromagnetic radiation, gravitational waves, or neutrinos emitted since the Big Bang. This volume, computed as 4/3 pi times radius cubed, totals approximately 4 times 10 to the 80th cubic meters. Within this volume, matter distributes in the cosmic web filaments, clusters, and voids, all causally connected through the universe's history. Objects beyond the particle horizon are not merely difficult to observe, but are fundamentally unobservable. Information from these regions hasn't had time to reach us. As we observe increasingly distant objects, we see them as they appeared at earlier cosmic epochs. At the particle horizon, we observe the universe as it was moments after the Big Bang. Beyond this distance, in principle, lies more universe, possibly infinite, but its light has not reached us and never will if dark energy prevents it. Light travel time to the oldest photons spans 13.8 billion years to the universe's age, though the distance travelled is only 13.8 billion light-years in a static universe. In an expanding universe, the relationship between distance and look-back time is non-linear. Photons travelling toward us cover less proper distance per year in cosmic time because regions ahead of them recede due to expansion. Early in the universe's history, when matter density dominated, expansion decelerated, causing photons to cover less distance per year. Later, when dark energy dominated, expansion accelerated, also affecting distance-time relationships. The light travel distance, the integral of c times dt over the photon's path, is 13.8 billion light-years. But the comoving distance, incorporating expansion, is 46.5 billion light-years. This counterintuitive result arises from space itself, expanding during transit, carrying the emission point farther away continuously. Expansion during photon transit means space stretched between emission and observation points while light travelled. Consider a photon emitted from a galaxy 13 billion light-years away shortly after the Big Bang. In the intervening 13 billion years, the space between that galaxy and Earth expanded significantly. The galaxy is no longer 13 billion light-years away, but rather 30 plus billion light-years due to expansion. Redshift quantifies this expansion, the photon's wavelength stretched by the same factor space expanded. A photon emitted in the ultraviolet might arrive in the infrared after being redshifted by factors of 10 or more. High redshift objects, like Z equals 11 galaxies, are now located roughly 30 billion light-years away, despite light leaving them only 13.4 billion years ago. This expansion effect must be accounted for when converting between redshift, distance, and look-back time, requiring detailed cosmological models incorporating matter density, dark energy, and expansion history. The number of galaxies in the observable universe is estimated between 200 billion and 2 trillion, with uncertainty arising from difficulty counting faint, low-mass galaxies below current detection thresholds. Deep surveys like Hubble Ultra Deep Field and JWST Deep Field resolve galaxies down to limiting magnitudes corresponding to roughly 1 million solar masses at Z approximately 6. Extrapolating number counts to fainter magnitudes using the galaxy luminosity function yields total counts. Early estimates based on Hubble data suggested 100 billion galaxies. Recent analyses incorporating faint galaxy populations suggest 2 trillion. This count includes all galaxies across cosmic time, from the present to the early universe at high redshift. The number density of galaxies declines. With redshift, fewer luminous galaxies existed in the early universe. Additionally, many high redshift dwarf galaxies merged to build the massive galaxies present today, reducing galaxy numbers over time through hierarchical assembly. Observable atoms total approximately 10 to the 80th within the observable volume, calculated from the average matter density 0.25 atoms per cubic centimeter times the observable volume 4 times 10 to the 80th cubic meters, yielding 10 to the 80th atoms. This accounts for hydrogen and helium comprising 98% of baryonic matter by number, with heavier elements contributing negligibly. The baryon density was determined precisely through CMB observations and Big Bang nucleosynthesis predictions, matching observed light element abundances. Baryons, protons, and neutrons comprise only 5% of total density, with 27% dark matter and 68% dark energy. If dark matter is particles, there are roughly 5 times more dark matter particles than atoms, though their nature remains unknown. The 10 to the 80th atoms distribute non-uniformly densely in galaxies, clusters, and filaments, sparsely in voids. Most atoms by mass reside in stars, with roughly 10 to the 68th stars each containing 10 to the 57th atoms, totaling 10 to the 125th atoms in stars, though most atoms actually reside in intergalactic gas. The Hubble volume defines our causally connected region, the volume within which events could have influenced us since the Big Bang given finite light speed and expansion. Objects within the Hubble volume share causal contact. Their past light cones overlap ours, meaning events there could affect us. Objects beyond are causally disconnected. We cannot influence them, nor they us. The Hubble radius, c divided by Hubble parameter, is currently approximately 14 billion light-years, comparable to the observable universe's size. In a decelerating universe, Hubble radius exceeds particle horizon more volume is causally connected than presently observable. In an accelerating universe with dark energy, Hubble radius eventually becomes smaller than particle horizon. Some presently observable regions will become causally disconnected in the future. This creates an event horizon, the boundary beyond which objects are receding faster than light due to expansion and will never be observable. Information limits prevent receiving signals from beyond the particle horizon. These regions are too far for light to have reached us during the universe's age. Even if powerful transmitters existed beyond the horizon broadcasting signals continuously, we cannot receive them. The signals simply haven't arrived yet. As time progresses, the particle horizon grows, bringing previously invisible regions into view. However, dark energy acceleration will eventually freeze the particle horizon. Accelerated expansion will carry distant regions away faster than light, preventing new regions from ever becoming observable. The combination of finite universe age, finite light speed, and accelerated expansion creates fundamental limits on what we can observe, learn, or contact. The observable universe represents our cosmic horizon. Everything beyond is, by definition, unobservable and unknowable through direct measurement, accessible only through theoretical extrapolation. Cosmic horizons and the unobservable universe. The event horizon, located at a co-moving distance of approximately 16 billion light-years, defines the boundary beyond which objects are receding faster than the speed of light due to cosmic expansion, and will never be observable regardless of how long we wait. This horizon differs fundamentally from the particle horizon. The particle horizon encompasses everything from which light could have reached us by now, while the event horizon encompasses everything from which light will ever reach us, even waiting infinitely long. Dark energy acceleration drives expansion to accelerate, causing distant regions to recede ever faster. Objects currently beyond 16 billion light-years are receding faster than light, not violating relativity because space itself expands rather than objects moving through space, meaning photons emitted toward us from these regions never reach us. They're swept away by expansion faster than they can approach. The event horizon represents our future visibility limit regions. Beyond will never be observable, even given infinite future time. Future visibility limits contract as dark energy acceleration increases expansion rate. Currently, we observe galaxies out to redshift Z equals 11 or higher, corresponding to co-moving distances exceeding 30 billion light-years. But these galaxies will fade from view over trillions of years as expansion accelerates and redshift increases without bound. Light emitted from them now, travelling toward us, will be increasingly redshifted and dimmed. Eventually, their light will redshift to infrared, microwave, and radio wavelengths, becoming undetectable. Simultaneously, the event horizon, currently 16 billion light-years away, prevents light emitted in the future from beyond this distance from ever reaching us. As time progresses, galaxies currently within the event horizon will cross it and become permanently invisible. In 150 billion years, the local group and nearby groups within roughly 10 million light-years will remain visible, but Virgo cluster and all structures beyond will have receded beyond the event horizon, disappearing from view forever. Dark energy acceleration means expansion rate increases over time rather than decreasing as expected from gravitational attraction. Observations of type Ia supernovae, standardizable candles whose intrinsic brightness is known at redshifts Z, approximately 0.5 to 1 inch, the late 1990 seconds revealed that distant supernovae appeared fainter than expected. indicating they were farther away than predicted by decelerating expansion models. This discovery implied expansion was accelerating, driven by dark energy, a component with negative pressure, causing repulsive gravitational effects. Dark energy comprises approximately 68% of the universe's total energy density, dominating over matter's 32%. The dark energy density appears approximately constant. It doesn't dilute as space expands, unlike matter density, which decreases as volume increases. Constant density during expansion means dark energy's total energy increases, driving ever faster acceleration. This acceleration creates event horizons and will eventually isolate the local group from the rest of the universe. The true universe size, the extent of space beyond the observable universe, is unknown but likely vastly exceeds the observable region and might be infinite. The observable universe's 93 billion light-year diameter represents only the part from which light could have reached us, a sphere centered on Earth, limited by finite age and finite light speed. But space extends beyond this horizon. Observations indicate the universe is flat within measurement, precision. The geometry of space is Euclidean rather than positively or negatively curved. Flat infinite universes remain flat and infinite as they expand. If the universe is indeed infinite, it contains infinitely many galaxies, stars, and planets beyond our cosmic horizon, forever inaccessible. Alternatively, if the universe is finite but larger than the observable region, estimates suggest it must exceed the observable universe by at least a factor of 250, based on limits from CMB observations, searching for topological patterns that would appear if the universe were small enough to see repeated. Features. Topology remains unknown. We don't know whether the universe is simply connected like infinite Euclidean space, or multiply, connected like a torus, or other shape where travelling far enough in one direction brings you back to your starting point from another direction. In multiply-connected topologies, space might be finite in volume, yet have no boundary. For example, a flat torus universe wraps space periodically, moving far enough in any direction, returns you to where you started, like moving on the surface of a donut, where left connects to right and top to bottom. CMB observations search for matching patterns in opposite directions that would indicate multiply-connected topology, but no matches are found, constraining topology to be either simply connected or too large to observe. Current limits indicate that if the universe is a torus, it must be at least 250 times larger than the observable universe, making it indistinguishable from infinite space within our horizon. Multiverse possibilities arise in scenarios where our observable universe represents one region in a vastly larger or infinite space containing other causally disconnected regions. Eternal inflation models propose that inflation, the rapid exponential expansion thought to occur in the universe's first moments, continues eternally in most regions, while ending in finite regions like ours, creating a multiverse of bubble universes. Each bubble experiences different low-energy physics due to different symmetry-breaking patterns in particle physics, yielding varied physical constants, particle masses, and forces. These universes are causally disconnected. No information exchange is possible, making the multiverse hypothesis difficult or impossible to test empirically. String theory predicts an enormous landscape of possible vacuum states, each corresponding to a universe with different properties. The anthropic principle suggests we necessarily observe a universe compatible with our existence, which requires fine-tuned properties like appropriate cosmological constant, stable atoms, and long-lived stars. Universes with radically different properties wouldn't produce observers. Observable volume totals approximately 4 times 10 to the 80th cubic meters, calculated from the observable radius, 46.5 billion light-years, and spherical geometry. This represents the region of space from which light and information could have reached Earth during the universe's history. Within this volume, approximately 2 trillion galaxies, containing 10 to the 80th atoms, distribute across the cosmic web in filaments, clusters, and voids. The vast majority of this volume consists of nearly empty intergalactic space. The average density is only 0.25 atoms per cubic centimeter, far less dense than even the best laboratory vacuums. Most matter and atoms concentrate in galaxies, particularly in stars and gas clouds. Voids under dense regions comprise 50 to 70% of volume, but contain only 10 to 20% of matter. Filaments and clusters occupy 30 to 50% of volume, but contain 80 to 90% of matter. This highly non-uniform distribution arose from gravitational instability, amplifying initial small fluctuations over 13.8 billion years. Total mass energy within the observable universe is approximately 10 to the 53rd kilograms, calculated from the critical density 10 to the minus 26th kilograms per cubic meter times the observable volume 4 times 10 to the 80th cubic meters. This includes all forms of energy: matter, dark energy, and radiation. Of the total, roughly 5% is ordinary matter atoms, comprising stars, gas, planets, and living things. Another 27% is dark matter, non-baryonic particles, interacting gravitationally but not electromagnetically, detected through gravitational effects but never observed directly despite extensive searches. The remaining 68% is dark energy, the mysterious component driving accelerated expansion. Ordinary matter's 5% translates to approximately 10 to the 52nd kilograms in atoms, or equivalently 10 to the 78th atoms. The observable universe's total mass energy is finite. Though the universe beyond our horizon might be infinite, we can only account for the finite observable region, reflecting on our place in the cosmos. The scale progression from humans to the observable universe spans approximately 28 orders of magnitude. An average human stands roughly 2 meters tall, written as 10 to the 0th meters in powers of 10. Earth's diameter is 10 to the 7th meters. The Sun is 10 to the 9th meters across. The solar system, encompassing the Oort cloud, extends to 10 to the 16th meters. The distance to the nearest star, Proxima Centauri, is 4 times 10 to the 16th meters. Our galaxy, the Milky Way, spans 10 to the 21st meters. The local group extends to 10 to the 23rd meters. Virgo cluster is 10 to the 24th meters away. The cosmic web's largest structures reach 10 to the 25th meters. Finally, the observable universe measures 10 to the 26th meters in diameter. Each step represents a tenfold increase in scale, and we've traversed 28 such steps from human to cosmic scales. This progression illustrates the vast hierarchy of structures, from microscopic to planetary to stellar to galactic to cosmological, each scale governed by different physical forces and phenomena. The Milky Way's position in the universe appears entirely ordinary, a typical large spiral galaxy located in a typical small galaxy group residing in the outskirts of a typical supercluster. The Milky Way is neither particularly massive nor small, containing 200 to 400 billion stars, comparable to Andromeda's trillion stars, but far exceeding dwarf galaxies' millions to billions. Our location within the Milky Way is similarly unremarkable, 26,000 light-years from the center, midway between center and edge, in a minor spiral arm between major arms. The The local group represents a typical small galaxy group. Our position on Laniakia's outskirts is typical. Most galaxies reside in superclusters' outer regions rather than in central rich clusters. This ordinariness confirms the Copernican principle: there is no special place in the universe. Earth is not the center. The Sun is an ordinary star. The Milky Way is an ordinary galaxy. Observations reveal no preferred locations or directions on scales exceeding hundreds of millions of light-years. The universe appears statistically homogeneous and isotropic, looking the same from any location. The Copernican principle, which states that humans do not occupy a special place in the universe, has been repeatedly confirmed through astronomical observations. Initially, Copernicus displaced Earth from the cosmos's center, placing the Sun there instead. Later observations showed the Sun orbits the Milky Way's edge, not its center. The Milky Way proved to be one galaxy among billions, not the universe itself, as many believed, until Hubble's 1923 discovery of Cepheid variables in Andromeda established its extragalactic nature. Our location in the universe shows no special features. We're not at the center of the observable universe. But every observer at every location sees themselves at their observable universe's center because they observe equally far in all directions, limited by light travel time. The Copernican principle extends philosophically to life and intelligence. There is likely nothing special about life on Earth, suggesting life arises wherever conditions permit, making the universe potentially teeming with life, though vast distances might prevent detection or contact. Cosmic perspective reveals Earth's size relative to the observable universe as vanishingly small. Earth's 12,742 kilometer diameter is approximately 10 to the minus 20th times the observable universe's 93 billion light-year diameter. Written as a fraction, 0.0000000000000000000001 or 100 billionth of a trillionth. If the observable universe were scaled to the size of Earth, our planet would be smaller than an atom. If Earth was scaled to an atom's size, the observable universe would exceed the actual observable universe's size. These comparisons illustrate the incomprehensible vastness of cosmic scales. Yet humans, through science and technology, have mapped this vast cosmos from subatomic scales through human scales to cosmic scales using mathematics, observations, and reasoning. Our physical size is tiny, but our intellectual reach spans the universe, from Planck scales to cosmological horizons, from 10 to the minus 35th meters to 10 to the 26th meters, encompassing 61 orders of magnitude. Human significance in cosmic context is ambiguous. Physically, we are insignificant, tiny, temporary structures on a small planet orbiting an ordinary star in an ordinary galaxy, in an unremarkable location in a universe containing trillions of galaxies. Our existence spans the briefest instant of cosmic time. Modern humans emerged 300,000 years ago. Civilization arose 10,000 years ago. And science flourished for mere centuries, all within a universe 13.8 billion years old and destined to continue for trillions of years. Yet we are the universe's only known conscious observers, matter organized into structures capable of understanding itself. Through science, we've decoded the cosmos's history, composition, and fate. We've traced our origins from Big Bang nucleosynthesis through stellar nucleosynthesis to planetary formation and biological evolution. We're made of star material, carbon, oxygen, nitrogen, phosphorus, calcium, iron, forged in stellar cores, and supernova explosions, scattered through space, incorporated into planets, and organized into living, thinking beings. Future observability will decline as dark energy acceleration carries distant structures beyond the cosmic event horizon over hundreds of billions of years. Currently, we observe galaxies to redshift Z equals 11 or beyond, corresponding to 13.4 billion light-years look-back time. In 150 billion years, observers in the local group will see only the merged Milky galaxy and nearby groups. Within 10 million light-years, all other galaxies will have crossed the event horizon and disappeared. The cosmic microwave background will redshift to undetectably long wavelengths. Future astronomers, if they exist, will have no direct evidence of the Big Bang, cosmic expansion, or the existence of other galaxies. They might conclude the universe consists only of their galaxy, eternal and unchanging. This loss of cosmic memory highlights the fortunate timing of our existence. We inhabit an epoch where the universe's history is accessible through observations. Earlier, before recombination, observations would be limited by opaque plasma. Later, accelerated expansion will erase evidence of cosmic history. Cosmic humility emerges from recognizing the universe's vastness beyond human comprehension. The observable universe contains more stars 10 to the 22nd to 10 to the 24th than grains of sand on Earth. Each star potentially hosts planets. The number of planets likely exceeds the number of stars. The possibilities for complex structures, life, intelligence, civilizations, and technologies scatter across incomprehensible scales. Meanwhile, dark energy isolates structures, preventing contact even if other civilizations exist. The universe's physical immensity is paralleled by its temporal vastness. Our few millennia of civilization represent 10 to the minus 10th of cosmic history to date, and infinitesimal fractions of the future, trillions of years. The humility from cosmic perspective is profound. We are extraordinarily small and brief. Yet this perspective also inspires wonder and curiosity. Understanding cosmic scales, from quantum to cosmological, represents humanity's greatest intellectual achievement. We are star material, observing itself. This poetic phrase, popularized by Carl Sagan, captures a profound truth about our cosmic origins and nature. Every atom in our bodies, except hydrogen, was forged in stellar furnaces or supernova explosions. Carbon formed through helium fusion in red giants. Oxygen formed in massive stars' cores. Nitrogen formed through CNO cycle processing. Iron formed in silicon burning before core collapse. These elements, scattered through space when stars died, incorporated into molecular clouds, collapsed to form new generations of stars and planets, and eventually organized into living structures. Life on Earth is literally made from stellar remnants. We are the universe's matter organized into forms capable of consciousness, thought, and understanding. Through science, this star material developed the capacity to trace its own origins, understand its nature, and contemplate its place in the cosmic story. We are how the universe knows itself.